Okay, so I would like to welcome all the attendants to this second day of the second workshop of the Energy Materials for Innovation initiative. This initiative, well, today we will be talking about the step from laboratory to engineering. And my name is Lorenzo Malerba. I work at CMAT in Spain, and I am the coordinator of the Joint Programme Nuclear Materials of ERA. And I will be chairing today the session together with Monica Fabrizio, who is the deputy coordinator in ERA of the AMPEA Joint Programme. In fact, in this initiative, many people are involved for the organization. It's an initiative that was somehow triggered by my joint program on nuclear materials, but the joint program AMPEA, which is on advanced materials and processing for energy applications, as well as the joint program on digitalization for energy, were deeply involved in organizing this initiative, with the participation of several other joint programs as well for the identification of the topics to be addressed. The idea of this initiative is to put material science a little bit in the forefront and look at the different aspects of materials from the discovery to the actual step, like in today's workshop, towards the industrial application, and then monitoring materials health, for example, during operation, and then having a look at the whole life cycle of materials and components. So to do this, a series of workshops has been planned. The first one was held on the 1st of July, and it was about materials discovery. This is the second step from laboratory to engineering. And there will be one that will be let's say, introduced at the end of the day today on digital twins. So this is about essentially the lifetime, in a way, of the components. And then next year, 3 more workshops are foreseen. One on the sustainability, so strongly related with the life cycle of materials and components, and 2 that will be more specific for classes of materials, namely materials operating under extreme conditions and catalysts. So today, as we said, we are in the second day of this workshop dedicated to the step from laboratory to engineering. There are 4 talks foreseen in the agenda. For each talk there is about half an hour, and in this half an hour basically we should consider about 20-25 minutes for the actual presentation, and then 10 to 5 minutes for questions. Questions will be through the chat, so whoever has questions should use the chat, and then Monica will take care to address the question to the speaker. At the end, so there will be these 4 presentations, and we will conclude the workshop and the session today with a panel discussion. The panel discussion will be chaired by Holger Issen, who is also among the organizers of this, the many organizers of this workshop and the whole initiative EM4I. And that will be basically it for today, and we will finish with the conclusion, drawing some conclusion, then introducing the next workshop. So without, well, before giving the floor to the first speaker, perhaps Monica wants to say a few welcoming words. Monica, please.
Thank you, Lorenzo. Yes, just 2 words. My name is Monica Fabrizio. I'm working at the CNR in Italy, and I'm very glad to participate and to be in the organizing committee of this workshop series. Just an outline. The present workshop is the logical basis of the last general workshop on material sustainability. In effect, the pathway from material in the lab to the materials and components and devices in the industry is the value chain that we will consider in the sustainability assessment of materials and process. Then this will be the subject of the next workshop. Thank you.
Okay, thank you, Monica. So I will give now the floor to the first speaker, Roberto Gianantonio. Roberto is adjunct professor at the University of Milan, Università degli Studi di Milano, and teaches patents and management of innovation. He's also a research fellow at the Consiglio Nazionale delle Ricerche, the Research National Council in Italy, and project manager at Globman International, as well as a freelance professional on technological innovation. So please, Roberto, the floor is yours if you wish to share your screen.
Yes, thank you so much. All right, so first of all, I really like to thank you all, and Sacco and Monica in particular, for inviting me today to this very exciting workshop and giving me the opportunity to share with you some of my thoughts about technological innovation in general. So, of course, I will go through also the step that you cited before that joins, I would say, the very research which is undertaken within the lab, going to engineering and industrialization of something that will become a product, hopefully. But this is a very particular, I would say, talk related to some organizational aspects of the technological innovation in general. And so this is the outline. These are just really some thoughts that I am thinking about these days, these months. And so my aim is really to share with you these thoughts. And so after a very brief introduction, I will talk about borders of an organization, how to chain TRL staircase steps, how is worth to balance and integrate competence within an organization. I will spend a few words about the ambidexterity of a research organization. I will give you some images, some shots about something I am thinking heavily these days, which are dissipative structures, concepts related to dissipative structures as applied to organization engaged in the technological innovation process, something about the flows of human resources within organizations, and finally a few words about entrepreneurship, what is a lean organization, and get into final comments. And very briefly, so I am, as we said, so yes, today I'm teaching and so, but my story is mainly in the industry. So I have a PhD in industrial chemistry, and I worked for 20 years in the industry, in a highly innovative industry located in Milano. This is a group, actually, this is a SciSgetter group, one of the most innovative companies in Europe, I would say. And so I spent the first 10 years there as a technologist mainly. So even if I am a chemist, my first work job was an engineering job. So I headed the engineering department within the corporate R&D of SciS for 10 years as a technologist. Then I spent 3 years within the corporate R&D by creating a new function called the knowledge management function. And finally, from 2008 to 2013, I played the role of corporate R&D manager for the group. And then I changed, I would say, my life in 2013, deciding to spend my my time more on the public side of research rather than on the private side, and so I had some experience as an innovation manager at a technological district in Lecce, which is called DTEC, which is an intermediary of knowledge. These are words cited yesterday by also Francesco Matteucci, and I am teaching, I'm lecturing, and doing many things. And now a very few images just to let you to share some aspect of my life. These are very special pumps, getter pumps that were integrated a time ago at the end of the 90s in a proton antiproton collider in Frascati. This is a very highly sophisticated getter pumps integrated into the beamline. So this was the first time in the history that a pump was directly integrated very close to the interaction point of the beams in a particle accelerator. And you know, I was engaged and involved in a large number of projects, industrial projects, and you know, I always started from the lab research, ending up eventually to a product, and so I managed quite a large number of patents. I am inventor of more than 25 patents, and these are just images. This is an ion mobility spectrometer that I invented a time ago. These are very special tools that I designed as a technologist to explore the parameter space of superelastic alloy education and shape memory alloy education. So this is a tool that create new knowledge. Basically, this is the role of this new tool, to automatically explore parts of the parameter space in order to understand how to process these nitinol wires in order to exploit the shape memory function of these alloys. And these are more recent works I was engaged to. This was and this is just an image related to the polariton technology. You know, I'm working in Lecce since 8 years at the Nanotechnology Institute of the CNR, where we have excellent competence. One of them is this one related to polariton physics. So I wrote a project, a ERC project, to try to exploit, to generate first demonstrations of possible application of this technology that apparently should live only within really highly explorative research labs. And this is another similar work that I was involved to, dealing with holographic microscopy, digital holographic microscopy. So these are just images in order to share, I mean, my word, basically. And so this talk is, I would say, the prosecution of a talk that I gave a couple of weeks ago at Nano Innovation 2021, where I wanted to discuss about how to manage innovation, take into account that I can say that it is possible to innovate, because for 20 years, this is exactly what I did. And so we succeeded. We have also, I also participate to projects that were not successful, but in the majority of cases, I would say innovation process was successful. So we have spent a huge amount of time and money and efforts in order to get a new product, and we succeeded. So I am sure that it is possible to innovate. The other question was in this Congress the question is it possible to innovate within the public research? Because in Italy, at least, but as we said yesterday, by citing the European paradox, it apparently is not so easy to innovate, staying from the public research side of the innovation process. And finally, I highlighted, as I still wanted to highlight today, that I mean, innovation must be taught. So we have seen yesterday that we do need to develop a culture within the member state of Europe, and we have to share this culture. This is one of the priorities I see with respect to innovation in general. So what we need first in general is to steadily, systematically, and continuously try and contribute to develop a culture of technological innovation. This is a key to improve our performance in exploitation of project results. And actually, what I wanted to stress is that, yes, innovation is a process, as we all know, whose output is something which is new, certainly, and useful. So either the output of the process is a product or a process, but the characteristic of this new process of products is that they have to be new with respect to the state of the art, and they must be useful. But another aspect of innovation is that this is seen by someone, in particular Peter Drucker, as a very specific function of the entrepreneurship. So innovation is not a practice living by itself, which is separate by other practices, aimed at creating value. This is a specific function of the entrepreneurship. So this belongs to the wider competence of entrepreneurship. And in general, now this presentation is focusing on the role of the organization within the innovation process. And in general, so we have to say, from the logical point of view, the innovator, and I mean with innovator, the innovation stakeholders which are engaged in a specific technological innovation process should clearly state the goals they wanted to reach. They should clearly state the time frame they want to get these goals. And when this is done, resources has to be identified, the resources needed to get this goal within specific project has to be identified and set in place. And generally speaking, among the various resources which are needed, two are particularly important, and financial resources first, and people there. So people is a key asset of the innovation process, and people have to be organized. And so borders, this is my first, something I want to share with you. This was something I thought for a long time in my life, in particular during my life in the industry. And, I started there in SAIS with a 4-people group. Then this group grew up to 22 people, including engineers and chemists and physicists and informatics and so. And then ended up with an organization of more than 60 people. And I had the chance to deeply reorganize the organization of the corporate R&D. And when I was entitled to do this, I decided to develop, let's say, a border organization, so a specific part of the organization devoted to the interaction with the outer world, with the environment. And for example, I will now tell you a few things about how I managed the revision, the deep revision of the technology portfolio of the group a time ago. And in order to revise this technology portfolio, I had to interact with the other world, at least to learn. And so I needed the people featuring specific skills to interact with the outer world and to bring information within the inner organization. And this is a very special people. For example, I needed to access a variety of European projects to establish connections and relationships with the prospect partners or prospect customers, or to try to exercise new value chains. And so I needed people able to do this, to take part to funded project. You may know that not all the people is the right people to take part to a funded project. You have to interact properly with the other guys, and so. And so this is a, let's say, border organization, one which is particularly adequate to connect the internal organization of the innovator, in my case, of the internal organization of the sales group, with the outer world. Collaborative projects actually are a key topic in my mind to improve the way we manage technological innovation. we see that also in this funding coming from the European Union and going to the several member states, Italy included, the great part of this fund is go into funding of collaborative projects. So these are particularly critical topic an organization must be able to enter into. The organization must learn how to access collaborative projects and take advantage of this funding. And this is one of the reasons that I also I am invited to teach to people, in this case to the Castellanza University, something about the collaborative projects. And border people is also extremely important whenever technology transfer is important. So, you know, this is one of the problems that the public research, the academy and the national research centers are facing when technology transfer is under discussion. Very often we see that there is no experience, no competence in dealing with technology transfer, and this is because organizations, and in this case, according to this slide, organization are the university of the research center, or a startup, a small and medium enterprise, or a large enterprise. All of these subjects must own a very specific organization that deals with technology transfer. Someone must be aware of what technology transfer is from the academic side in order to bring technology to the attention of prospect buyers. And the same happens for the small and medium enterprises. A specific organization must be set in place in order to establish a relationship and a contact and a dialogue with technology owners in order to access the technology that may be useful to undertake innovation initiatives. And I mean, technology transfer is extremely important process, one that mostly characterize the open approaches to innovation. You take into account this is how John Besant for the Imperial College represent the whole innovation process. You may be aware of this four-step stage, and this is an extremely powerful representation of the innovation process. And the process starts with a search phase. So we do not have to conceive internally ideas about a possible product to develop. We may catch ideas from wherever we have a chance to find it. And so the search phase it must engage border people, which is able to catch opportunities and then participate to the forthcoming stage, which is the selection of new ideas. And so you may imagine that in order to properly play an open approach to innovation, according, for example, to this representation of Besant, you need very specific people, not excellent people working in the lab, but the people that has the capability to take part of the search process. People that is available to implement innovation initiatives that are not just based on the exploitation of the very technology, but may take advantage of new ways to do innovation. And this is an example of a new way to do, rather new way to do innovation, which is the design-driven innovation invented, I would say, by Roberto Verganti of Politecnico of Milano. And this way of making innovation opens up a huge scenario for applications, because you should, I mean, think that you may be able to generate a new product whenever you are in the position to assign a new meaning to this product. An example of this, we cannot go deep into this, but an example of this you may know is given by Nintendo's Wii, that is a main case of design-driven innovation, where there is a concurrence of contribution to the success of this initiative, the Nintendo initiative, from the side of reassigning new meaning to the product, and both from the side of implementing in the product a new technology. In this case, you speak about of a technological epiphany. So you give a new meaning with new technologies to the product. So example of, so I just finished to spend a few words about a very specific part of the organization, border organization, that do something which is extremely useful to manage properly, to manage it at the state-of-the-art the innovation process of the border organization. Now, another thing, something I think often is how to chain the staircase step of a TRL technology readiness levels chain. So this is we know this way of dividing the evolution of a technology, the degree of development of a technology, starting from science. So at the TRL1, you have the very science, and you will typically end up with the market when you provide market to the customers, and you go through 9 of these steps that you can group in 3 macro steps. One is, I would say, the research steps, then you have development or engineering steps, and then you have deployment or market steps. And something which is extremely important, if not necessary, is to enchain, is to closely connect these steps within an organization. This is one of the reasons why, for example, the academic research does not succeed in innovating, because typically in academic organization, you just find researchers which are focused on science. Very rarely you find within an academic staff engineers or even more people that take care of business development and relationships on the market and look for applications. So what is needed is to, in general, establish organization where you can enchain these steps from the science to the market. And this is just a flash, an image dated 97, and the guy at the bottom right is myself. So this was 24 years ago. I started from designing a new solid solutions made by mercury, which was infiltrated into the octahedral site of a titanium lattice. So we began with laboratory research to explore new ways to stabilize and destabilize mercury in order to make mercury dispensers for the fluorescent lamp industry. But then I directly took part to the engineering phase, where after the demonstration of a proof of concept, yes, this alloy is working, mercury can be released properly with the accuracy and the timing which is requested by the final application, but then we have to manufacture this product. So at the time, I had not yet this very large group of people dealing with technology, so I took directly care of this engineering phase, and this was a key of the success. I could personally bring the knowledge we have developed within the research into the next phase, which is now we have to prototype it, we have to design the tools that we may use to deploy mass production of these products. This was another message. Organization, typically to be effective in the technological innovation process, should engage people that take care of these different macro steps. And so, stated in other words, we have to balance and integrate competence within research groups. We have seen yesterday Martine Main that talked to us about her experience in the startup, and she disclosed how this competence grew during time up to the point that an application was clearly identified, and then also the standardization of the product and the engineering aspect of the development were properly managed, and so people could access the market and so. So typically the organization, and this is particularly what we can say, that this should be an effort by the public research and small and medium enterprise. These organizations should be structured so that we have either the
3 minutes, Roberto.
10 minutes. Yes. So
5 minutes. 5 minutes
we have
maximum.
either science and either technology, either engineering, and either the management competence. Yes, so technology is something which is highly different with respect to research, because technology generates systems, prototypes, proof of concept, and finally products. And the concept of technology is not so developed in the public research. Researchers are not properly aware even of the very meaning of a technology, which is so different with the meaning of science. Technology must be described, properly described, and this also occurs rarely within public research centers and even small and medium enterprises. Applications must be targeted in order to address the exploitation of a specific technology towards a specific system, which eventually may become a specific product. So also the applications must be targeted. And so a research organization should be feature ambidexterity. Yes, must be engaged in explorative research, but also must be heavily engaged in the identification of applications, because applications drive the focusing of technologies. Ambidexterity, let's use the existing technology. We are not forced to create necessarily new knowledge to undertake innovation. Just give a proper look to the existing technology and try to take advantage of what you already have. Also using specific tools, so simulation tools, for example, or tools that are so rarely used, such as trees, for example. This is a way to innovate, and ambidextrous organization should develop some competence also in this field, in my mind. A description of the processes that generate a new product, representing the product as something featuring properties, functional properties, a given number of functional properties, positive properties of negative properties. This is enough to launch a product development phase, but you have to abstract from a very specific case, and to just understand that if you work on this theoretical representation, you have the chance to see how you may improve products and launch new innovation initiatives. This is a case. Now in 3 minutes, I finish with 2 examples. This is a case that I managed time ago. I call this, not only myself, of course, this is a fusion innovation, is a case where you can just take care of the integration of technology. You do not have to develop brand new technology, but identify existing, even mature technology and manage the integration to provide a new product. And this is a case I lived time ago. Also, today we may devote some time to explore new way to do innovation. This is a representation we will have to discuss separately, and but maybe way to manage innovation that are inspired by the work of Prigozhin and co-workers. So works the work of Prigozhin belonging to so-called dissipative structures. So these are systems that may create unexpected features. So these are concepts that may be adapted to novel innovation processes that are absolutely innovative, because they are not deterministic. You are not able to expect what will come out from this process, but you are with a certainty that something will come out.
Roberto, we should close, because otherwise there will be no room for questions or
2 examples of yes, I mean this is an example. Ecco, when we were in sales, we were forced to find out a way to develop new product for the organic light emitting displays. We developed from scratch new technology and followed according to a deterministic model the product to be developed according to specific technology. And we set up a specific context to do it, but in this context I had the power to enable the emergence of new shapes. And one new shape is this society that has been set up recently, which is called the sales coated film, that no one expected to set up because this was not the target, but the context that we created time ago enabled the emergence of this new company. And the same we can say for a new venture, which is called Flexterra. So in 2008, I created a new context aiming at developing light emitting transistors for the flexible display industry. An unexpected result was to buy the whole patent portfolio of EERA Corporation, that was the strongest developer of competence in organic electronics at the time and still today. And so from this context, unexpectedly and according to non-deterministic processes, we had the chance to buy the EERA, to embed a patent, very large patent portfolio of 160 patents, and be the first actor in the development of products for the organic electronic fields. Entrepreneurship.
Roberto, you should.
I have finished. Thank you for your kind attention.
Thank you. Okay, so we have very little time for questions, but I think there is one, perhaps, Monica.
Yes, there is a question from Mark Kozras. Interesting question from Roberto, obviously. For Roberto, mobile phones like iPhone have a good understanding of form, function, and meaning. How can we make a clean energy solution that is not held in our hands increase its personal attachment to a product manufacturer or the public itself? Wow, it's a very complicated question. So can you rephrase? I mean, okay, I understand what a cell phone should be today, but what is exactly the question?
Okay, I can maybe clarify really quickly. Sorry, I'll just come on. Really, it's this. When you talked about form and function, I thought right away when you followed it with meaning in the one slide. I sat there and I hold my phone and I have such an attachment to my phone. Attachment is meaning. What drives the meaning that forces me to look at the attachment to that phone? Now, when we are working in the clean energy field, I'm finding magnetic materials that go up in a renewable energy wind source, or magnets for motors in a car that are hidden, not touchable. I can't touch those. And so the meaning becomes a different meaning. And I was trying to explore what you meant by meaning.
Oh, yes, it's not up to me. I mean, so these are concepts by Roberto Berganti, I told you. But for example, an idea of meaning, you know, which is the difference when you hold in your hand an Apple iPhone or a Samsung Galaxy phone. So when you keep in your hand an iPhone, you belong to a group that share the very same aesthetic or ethical values. So the meaning of this phone is linked to the fact that I belong to a group that share the same set of value, either of an aesthetic side or an ethic side. So for example, if I choose to buy a bag made with a canapa, I will do this because I want to be part of the community that believes that these kind of products has to be made by bio-based sources, not to impact too much onto the environment or so on. So you can attach to these products meanings that let you live specific emotions or sensations, or that enable you to participate to specific experiences. So when you go to a Starbucks coffee, you will not go there to drink a coffee, but you go there to buy a few minutes in your kitchens, in your home's kitchen. So you wanted to leave the emotions that you typically leave at home when you drink a coffee at your home. So this is the product, not the cup of coffee, but the 5 minutes of wellness that you have the chance to leave whenever you go to the Starbucks. And the same is for Amazon Go. When you go to Amazon Go, you do not go there to buy, I mean, a pair of shoes. You go there to live the buying experience, which is offered by Amazon Go. This is what you are buying, this experience, the way of feeling. And this is largely unexplored in the innovation field. So
thank you, Roberto.
That,
yes, thank you. I think we need to move to the next speaker. Okay, I actually wonder how we can transfer this to materials, but this would be a long discussion.
It's quite difficult, I think.
Yes, just look at the iPhone, which is full of materials.
Yes, but the materials come before the iPhone. But anyway,
they stay in the value chain.
So I think we need to move to the,
of course, you cannot do the
next speaker. So chain. Please, can you, Roberto, stop sharing so that we can allow Eva to share her presentation. And Eva Peterson is Head of Research and Innovation at SSAB. Where she has been working since 2006, and is especially now involved in the fossil-free steel journey and hybrid initiative, and she's going to talk about this hybrid initiative indeed now. So please, Eva.
Thank you very much. Now, can you hear me? Now my computer is...
We can hear you, but we do not see the presentation for the moment.
Now, my computer says no in this. So I can start by talking. Thank you very much for the introduction, and thank you for inviting me. I want to share SSAB is a steel manufacturing company, and I want to share with you how we are working with innovation, actually changing the way we produce steel. The way we produce steel from iron ore has been around for over 1,000 years, and we are now innovating and changing that. And the driving force for us is climate change, and the fact that the steel industry emits 7% of the world's collective CO2 emissions. So we want to address that. And my computer is still...
Perhaps if you cannot share the presentation, I think we have the backup. So perhaps Sako can share the screen and...
Okay, give me a second.
And put up, yeah, so...
I'm not sure I sent my presentation because I finalized this morning. Sorry.
Okay, I don't know. Because we have a few, but I don't know if you have all of them.
Okay,
I have not sent it because I did not receive it, Scalia.
No, because I finalized.
But if you could send it, Eva, if you could send it to...
Yes, I will do it. I will do it. Sorry for this. And we practiced before the meeting and everything.
Yeah, it was working.
And just speaking while I'm trying to do this at the same time. I mean, this is a practical example, and listening to the former speaker, a practical example of how and the key success that we feel and I feel is bringing innovation and what we can see in the laboratory to actually full scale, and in our case a full transition of a steel company and the production system that we have. It's a huge undertaking. It's a lot of money, and it's a lot of kind of and I will come to that, a lot of collaboration, and that you need to be you dare to do it. So I think I will compliment the former speaker in a good way.
So Are you sending your presentation to
Sorry.
Kalle, or?
Trying to.
Because otherwise, I suggest we swatch the presentations if there's a problem here.
I don't know why this is. I will have less time to speak to you. Yeah, if the next speaker is ready, maybe that is a good idea. Now I've taken already 5 minutes.
Yes, is Joachim in the audience? No.
Tommy is.
I don't think he's in the.
No,
Yes,
I'm
here.
sending it to you.
Okay.
I'm sending it to you, Kalle. Let's see if it receives. Sorry for this. It's still. I'm in a hotel, so maybe it's something with the connection. But it's good that you can hear me, and I can hear you. But the screen is white in the meeting. Do you receive it, Kalle?
No.
Maybe it's too big.
Well, it's 10 mega, it's no problem. But Lorenzo, I suggest you go to Tommy.
Okay, we can
And you
reshuffle then the order because I don't see Joachim. So Tommy, are you ready to give your presentation now?
Yes, I'm ready.
Okay, so sorry for this technical
I will try
problem.
to leave the meeting and go in again.
Okay. Okay, so then we move to a somewhat different example. So Tommy Lindros is a research team leader of Sustainable Materials Design, of the Sustainable Materials Design team at VTT in Finland. And he's going to talk about from powder to product. So it's an example basically that he's going to give us. So please, Tommy, the floor is yours.
Thank you. Introducing Lorenzo. So my topic is today to describe the, let's say, challenges and ways of working. We are scaling things from powder to products in the additive manufacturing process roles. And the special topic today is some examples about the optimization of the magnetic materials and the electromechanical components. And why the electromechanical components are interesting today, of course, it's connected to strong electrification, both in the process industry and also to electric mobility. So if we think about the changes, what has happening in the past years, of course, there is a strong increase or forecasted increase both in the electrical vehicle sides. We also expect that the electrification of the industrial processes are taking place, such as this SSAP hydrogen process needs a lot of electricity to produce that hydrogen, and simultaneously the production price of the wind energy has decreased sharply. So that enables to use the green electricity in many applications. But if you look at those numbers here, so it looks that the estimated that the wind energy production capacity will increase during next 5 years, so almost doubled. But simultaneously, only for electrical vehicles, the amount of electrical vehicles is 6 times higher in 2025. So it's quite easy to understand that there will be a huge demand for new energy and especially this green electricity. And one important thing is also to understand now that especially in the case of electrical mobility, the public discussion is really heavily focused to the batteries. But less attention has been paid on that how the electricity first is produced, and then how the electricity is transformed to moving cars, for example. And there is some dilemma between these two things, because both wind energy, for example, and these electrical vehicles motors, they are utilizing the same raw materials. So there will be huge demand for certain kind of raw materials, especially of course these heavy rare earths connected to the permanent magnets, but also other material like copper in copper windings, windings of the motors, and also in the the networks where the electricity is moved from production place to the, for example, charging stations. And this demand, we cannot solve that by recycling, because the increase of demand is so high. And we have to remember also that the life cycle of these electrical machines like wind turbine generators, that could be 30 years. So it takes 30 years to get back those materials back to the process. So meanwhile, we have to find new resources for those, or we have to somehow change the consumption of these materials. And we have started to study this problem from the reason that how much it's possible to decrease the weight of these electrical machines. And our vision is that 30% weight decrease should be possible when we are utilizing totally novel designs and also fully utilize novel manufacturing methods without those constraints which are conventionally connected to manufacturing methods. And of course, we have to keep all key characteristics, reliability and energy efficiency of these motors at least on the same level than current standards are. And what we can do, of course, we have to make some kind of innovations, how we should change the design principles, what are the possibilities on the new manufacturing technologies. And freedom of design is probably the most important issue in this dilemma. So, for example, our approach is heavily connected to the additive manufacturing road. So we can ask that how additive manufacturing can change the design principles of electrical machines. And for what is then needed to tackle this solution? Of course, we have to have really good understanding about the electrical machines, tools to design and analyze new electrical machine topologies. But then also we need the novel materials which are fulfilling those demands of the designs, and materials should also fulfill demands of those manufacturing methods like additive manufacturing. And then we need also, let's say, out-of-box design thinking, how to utilize the additive manufacturing, and for example, utilize a different type of optimization tools to generate new topologies for those electrical machines and electrical components. And finally, of course, we have to be able to also make a demonstration and prototypes to test our new designs in practice, and that way to be able to provide solutions for industrial partners. If we then think about what that it means, of course, I mentioned already this design thing, that what is needed to design novel electrical machines. I will have come back to that. But what are needed, we will need the whole processing chain from raw materials to ready-made components, and some kind of piloting facilities where we can produce those raw materials, powders for additive manufacturing, modify those powders suitable to different additive manufacturing process, then additive manufacturing itself, after the additive manufacturing, typically components are not ready. So different type of post treatments like heat treatment should be developed to get the full performance out of those components. And finally, we have to have environment and testing capabilities where to test those components. And in addition of this experimental road, it's really important that we are developing all the time the modeling capabilities for different stages of the process. Starting, of course, from the material development, what kind of material compositions we should use to maximize performance of the materials, how those materials are performing in the additive manufacturing process, for examples. How about the defect structures, how they are affecting the final performance of the component. And this type of parallel approach, doing simultaneously experimental work and the modeling work, that of course that speed up the development process, but especially that provides much more deeper understanding what is happening on different stages of the process, and can explain also the sometimes rather complicated phenomena seen in experimental characterization, for example. And that we are rather lucky that we have now established that the experimental route from the powder synthesis to component performance testing, and also working a lot with this modeling issues. And I hope that it's in coming years we can say that we have this type of virtual twin between these experimental and modeling activities, and speed up the development process remarkably. Okay, then if we got look at that, what we can do by this integrated computation and material engineering. So as I mentioned, it's really important to have these modeling aspects. Of course, the amount of different alloy compositions is huge, but by modeling and simulation, we can screen hundreds of thousands of different compositions to get the desired properties for the material. But one important issue is also that we can see by modeling the issues, also visualize the issues, for example, from laser powder bed fusion process, what is really happening in the powder bed during the laser heat exposure of the both powders. So those things are typically rather difficult to see in experimental processes, but it's much more easier to see those on computer screen. And similarly, we can check also what is happening in the microstructural level of the materials. Then if we first create the material, we can make the virtual model of the microstructure and start to, for example, make a virtual testing, like a virtual fatigue testing, and to see how those different type of defects, for example, affect, for example, fatigue life.
Med Joakim Antonisson. Ja, this is new.
Kalle, you are not muted. So probably
Presentatie for the workshop.
Kalle, can you mute your microphone, please?
Okay, then if we think more general, that what is this meaning when we are talking about the development step from powder to product, especially in the additive manufacturing. It's the general, it's not only connected to laser powder bed fusion. I think that these same steps are needed, for example, powder jetting, but I think that these five steps are repeated in all cases. Of course, how deep we should go in each step, that depends totally what kind of material we have and what is the maturity level of the area. But everything is typically started from the material selection. If there is some standardized alloy available, of course, it's much more easier to start to tailor that material to the additive manufacturing process, or then we start to totally discovery of new type of the materials. And then the next step, of course, is connected to powder processing, process development, both first on the powder and the modification of the powder suitable to the selected additive manufacturing process. And after that, we have the gate one, where we have to make a decision that are we fulfilling the demands of the process with that powder. So there's a lot of things connected, for example, flowability of the powders, and of course then the microstructure, what we generate during the process. And the number 3 step is connected to process parameter optimization. Okay, it's connected once again to the different processes. In laser powder bed fusion, it's a really rapidly cooling processing environment. So there is a lot of really complex parameters happening during the process. And after that, we will need the characterization of the materials to check if the processing parameters lead to desired properties. And in rather many cases, we are not able to say that totally after the step 3. We need also to include the post-processing of the components to evaluation of that. Because, for example, heat treatments are changing a lot of the material properties, and especially now when we are focusing on these magnetic materials, the heat treatments are really important. So we are making some kind of compromise between magnetic and mechanical properties by heat treating those samples. And then when we have made these processing parameters, powder processing steps, we are ready to start to design those real or test components to the testing and demonstration capabilities. This is the one example about the powder manufacturing. So now when I mentioned that if we are focused on the standardized alloy, now we have focused on 3 different types of standardized alloys, 2 iron cobalt based soft magnetic materials, and also one iron cobalt vanadium contained soft magnetic alloy. We have produced those powders first at the VDT powder piloting facilities by gas atomization, and have studied what are the properties of these powders, what is the particle size distribution after the gas atomization process, what is the yield of the gas atomization process. Particle morphology is one key issue when we are looking at the good flowability of the powder, and typically some kind of modification is needed. So the powder is classified between the certain particle size distribution. In the case of our laser powder bed fusion system, typically it's something like 15 microns to 63 microns, what we are looking for. And of course, then the composition, what is happening during the atomization process, is that there's homogeneous chemical composition on different size of particles, for example. Because if there is some evaporation, for example, then that could be so that the small particles has different composition than the bigger ones. And of course, if you think about what is take to make one batch of atomization in the laboratory pilot scale, make all these analysis of the powders, and then for first printing experiments, I would say that the 1 week is the minimum. Typically it takes 1 to 2 weeks to make the whole, that is one step and to have evaluation that what was the outcome of that material. And to speed up of that, we have developed some processes that we don't have to need the powder in really first stage. So we are utilizing the bulk samples and to make some kind of laser studies that how laser interacts with those materials. That is there, for example, happening some cracking or separation of phases during the laser exposure of that material. Then if we think about this, today's topic, that what is the meaning to move from the lab to the engineering, I think that in the additive manufacturing and the powder road, the first challenge is connected when we are moving from laboratory pilot scale operations, where the batch size is approximately, in our case, is the 5 kilograms. And if you like to move the bigger batches, which is needed in the larger additive manufacturing equipments, I think that typically if you go to the, let's say, the industrial size of printer, you will need at least 50 to 100 kilogram of the powder. And to get that powder patch somewhere, that is really limited. So if you can see this, these are showing the size effect, what is happening when the gas atomization equipment size is upscaled from 5 kilos to 10 kilos and finally to 500 kilos. You can see that the final 500 kilogram melting capacity gas atomizer is not anymore connected to research laboratories. It's let's say some kind of pre-industrial level atomization units, and also the moving from 5 kilos to 10 kilos. That means also approximately 4 times bigger place needed for the atomization unit, and meaning also that the costs are increasing rather sharply. So when we are moving from the small scale to larger scale, it's happening really quickly that money and time is consumed. So we have to be rather sure before to that step to move from the, let's say, the laboratory pilot scale to the next scale. And typically the next scale is not the 10 kilograms. It's needed something like 50 to 100 kilograms to move forward. Okay, then when we have the powder ready, the next phase is the actual additive manufacturing and the finding the optimal parameters for the additive manufacturing. And it's pretty much connected what we are looking for. The most typical case in the additive manufacturing parameter optimization is looking the porosity of the material. And of course, the porosity is also connected to the mechanical properties and partly also the magnetic properties in our case. But if you have something like 1% porosity, that could be also beneficial for the magnetic properties. So we have to utilize some kind of multi-parameter optimization. So looking all of those parameters simultaneously and then select the best possible candidate parameters for the printing job. And depending once again what we like to measure, we need the different type of samples. We need also quite big amount of samples because those post treatments and heat treatments development. So typically it has been done so that first we are optimizing the microstructure based on the metallography and studying also how the heat treatments are affecting of those microstructural features, and then to move to measure mechanical and the magnetic properties of these materials. And as mentioned, the heat treatment is really important step also in the additive manufacturing side. And one special feature is that you are not able to typically use, let's say, the conventional heat treatment routes for even those standardized materials. And that's because after this laser powder patch fusion, the structure is more or less like welded structure. And the main question is that how to normalize that type of structure. And as you can see, there is also rather big differences between small materials with small differences in the chemical compositions. For example, when we move this binary iron cobalt alloy to the iron vanadium alloy, you can see the as built conditions change totally. So the grain size is totally different in that case. And also the same heat treatment affects totally different way to the material, which has only 2% difference in vanadium content. And probably the most difficult thing in the optimization of this heat treatment cycle is connected that how to homogenize that structure so that the achieved microstructure is independent of the size of this component and also the fall thickness of component. So that we can say that in every time when you are using this type of heat treatment for this material, you will get the same results out of your system. Then after those optimization of those microstructures, you are ready to move to characterize the materials. In our case, now we have looked at the microstructure, how the microstructure is affecting on magnetic and mechanical properties. And then in the case of the standardized alloys, of course, it's nice to compare the results to the standardized alloys properties. If you have totally new material composition, of course, it's much more difficult to see how close optimum you are. But this is the one example after the, let's say, quite a heavy optimization of work of the first the additive manufacturing process parameters, and after that the heat treatment cycles. We have finally achieved the same, let's say, the almost same magnetic characteristics and the mechanical characteristics than the standardized iron cobalt vanadium alloy. But if you think then the typical electrical machines, they are consisting of, for example, laminated steel, electrical steel structures. And now when we are utilizing the laser powder bed fusion, the components are bulk components, and which is causing some problems with the eddy currents. So the next step is to start to think that how you can mitigate these eddy current losses when you produce materials by laser powder bed fusion. And there is 3 ways to tackle that problem. First of course is connected to the material, and if you can provide the higher electrical resistivity to the material, then we can decrease the amount of eddy current losses. Or then we can make some kind of optimization for the structures, or the final third process, or we can combine all of these the same using the additive manufacturing process, enabling the multi-material processing. And in this example, we have now utilized these 1 and 2 options. So first increase the electrical resistivity of the material by alloying, and then to optimize structure so that it mitigates these eddy currents. And this is really simple type of approach now shown here. So it's just perforated structure with really small slots preventing the eddy currents. And if we look at then how it affects to the material behavior under AC magnetic field, if we look at that in the case of the bulk component, the power losses at 50 Hertz, they are something like 29 watts per kilogram. When the laminated reference material has the power losses 3.6 watts per kilogram. But after some optimization roads, by utilizing this alloying effect and also this type of the optimization of these perforation of those components, we can decrease the power losses almost the same level than this laminated structure. And this work is ongoing, and now we are utilizing the topological optimization tools to design this perforation for these structures. And then the next bigger challenge is connected to the step that when we are moving to small scale laboratory additive manufacturing equipment to the industrial scale production system. For example, at the case of the VTT, we are utilizing the SLM125 machine, and I think that the industry is now more or less connected to this that's SLM500 machines. So when we increase the build envelope from 25 millimeters to 500 millimeters, that means that in practice, that needed amount of powder is increasing really sharply. So we need at least 25 times bigger amount of the powder to make a testing with the machine. So that is connected to powder availability. But then also the process parameter optimization is something what is really important to understand. When the size of the bed is increasing, you probably need to some kind of optimization of those parameters. What are the laser parameters in a bigger machine? There is a clear difference between small and bigger machines. And then it has also connection to the post-treatment. So if there is for example, the bigger machines, the heat load of those components can be higher. So that affects to the as-built microstructure, and that future it affects also the heat treatment. So in worst case, of course, we have to make a re-optimization also of this heat treatment cycle. And then when the size of these components is coming bigger, that probably have also connection to the need of different type of heat treatments. So as an outcome of this challenge, I would say that the final optimization should be done in correct phase of the project, and also, if possible, in the correct scale. So if you are targeting a certain size of components, you have to make the final optimization on same scale.
1 minute, Tommy.
Okay. And then finally, you have go through all of those steps. You have designed powder and produced powder. You have correct process parameters, both for the additive manufacturing and heat treatments. You have development strategies, how to mitigate magnetic losses. Then you are able to start the topological optimization of the final shape of the component, and then determine the shape of the additive manufacturing part. And finally, you have made the part, you are able to start the demonstrations in the selected scale. So this is now the example of VDT pilot scale demonstration facilities in the electrical machines. And then last slide. So the results are partly connected to two upscaling projects ongoing, founded by EIT raw materials. So the SOMA project is connected to the upscaling of the soft magnetic alloys for additive manufacturing. The 3D RIMAC is connected to 3D printing of rare earth permanent magnets. So thank you.
Thank you, Tommy, for your very, very interesting presentation. This is the question time, and there is a question from Anthony Boazio. The question is, what did you think about yesterday's MAP for the optimization of these parameters? If you, obviously, if you assisted to the first day presentations.
Yes, but I have to say that I can't remember exactly what was the.
Is a material acceleration platform.
Yeah.
Okay.
Yes, that was really nice idea, and I think well connected also to our ideas, and I think that the very important issue is that how we can combine the modeling and the experimental facilities, and there is also need some kind of high throughput experimental work to answer also demands of the modeling parts.
Okay, thank you, Tommy. And Mitwa, I have two questions for you. The first one is, how long the entire development and validation of the process needed?
It depends rather much, of course. If the, for example, if you think about the additive manufacturing process parameter, finding the correct process parameters, if you know the material group rather well, typically it's 1 or 2 test trials, and we have rather good parameters. And for example, if it's totally new material and it's not, for example, these rare earth magnetic materials which are rather brittle, it takes much more long time to find the parameters leading to the desired properties of those components. But I would say that it's one day, or it could be a couple of weeks.
Okay, and the second question is, in your opinion, who are the players of this preliminary process of development? The industry or the public research, like you, for instance?
Yeah, that's a good question. I hope that is cooperation. Of course, we like at VDT, we are working all the time close cooperation with the companies. So, for example, this upscaling process, there are companies behind the upscaling. But of course, I think that the first ideas are coming quite often to the research side. So of course, then if you have your own lab, some kind of piloting facilities, and you can generate components in relevant scale and show those to the industrial people, it's much more easier to understand what we are looking for and start to cooperation.
The competencies of yeah. Thank you, Tommy. There is just a chat in the chat. Mark Kozras has many ideas about the application of MIPs and would love a discussion of this with you, Tommy. Therefore, you can chat with Mark. Thank you again, Tommy. And now we come back to Eva Peterson. Eva? Are you ready?
Yes. Can you hear me?
And
I'm typing nothing now, and maybe you can show my presentation. I don't dare to touch the computer now, but you have it, right?
Yes.
So I will do share screen then. And then you will have to tell me. I hope there's not too many animations that gets complicated. Okay, I will do it share screen.
Do it in presentation mode, and you will be fine. It's not complicated.
Perfect.
Yeah.
Perfect. Okay.
So thanks again. And again, I am going to speak. I'm representing a company that now is together with other large enterprises, taking an innovation or a lab understanding to a full-scale production system. So with that perspective, I don't see the screen now.
I see the screen on my, may take a minute.
Am I the only one who doesn't see the screen?
No, you're not the only one.
I can see
Sawako
you,
Sawako is sharing.
See if we take a minute in, because I also sent it to Lorenzo and Monica.
Sako, can you share?
I don't have the file.
Oh, sorry.
It was too big for you. But Monica,
okay. Just a moment.
Now my pictures need to be very, very good. We've been waiting for a long time for them.
No problem.
should I do stop sharing here then?
Yes.
No, I don't share anymore, I think.
Okay. Can you see my screen?
Yes.
In presentation mode now?
Yes,
but that's not the beginning. It's not the beginning. So
yes, sure. Sorry.
You're in the speaker mode. You need to switch the screens.
Yeah.
So I want to talk about, I am from SSAB, but I want to talk about Hybrid, which is a joint venture that we have together with an ore company, that's LKAB, and an energy company, that's Vattenfall. So Hybrid is a joint venture, and I'm representing one of 3 owners, and that is SSAB. And as said, we're a steel maker. Next picture. So let's do it like this, maybe. Why is SSAB converting? Why are we driving this? Because it was actually on our initiative that this started. We recognize the global warming and the fact that it's preliminarily caused by the CO2 released from fossil fuels. And the steel industry accounts for 7% of the global CO2 emissions today. And most part is, of course, from the virgin ore-based steel manufacturing. The growing population, we understand that there will be more steel needed in the world. Also, steel is stuck for a very long time in user phase, so the scrap demand will not be enough. Next picture, please. We recycle, steel is actually the most recycled steel in the world. It compares to nothing else. And the fact is that when you recycle, you keep all the characteristics of the steel. It goes back to its origin. So it's a very good material to work with in recycling. And actually, recycle rate is about 85% in the world. But again, the demand will be much more in the future. Next picture, please. The demand will grow. If we were in 2016, we used about 1,600 million tons of steel a year. We predict, or it is predicted, that by 2050 we will need 2,500 million tons of steel per year. And given how much scrap is available, we will still need to do produce steel from iron ore even in 2050. Actually, the amount of steel we need to produce from iron ore 2050, the prediction is more than we do actually today. So next picture, please. We need to find some other more sustainable way of producing steel. Next picture. Now you jump to. And I will go into the basics of producing steel, but it is a way of producing that has been done since the beginning. It's using coal, which means that the byproduct is carbon dioxide. In laboratory scale, it's been known for a long time that you can use hydrogen instead of to replace coal, but you need a lot of electricity, and the industrial logic has not been there before. But given that Sweden has a large surplus of fossil-free electricity available, and also a large potential to build more wind power mills, Sweden and Finland are very good in R&D. We have a large pool of competence, both within the companies, but also in the institutes, VTT, for example, and the universities. And we have a long tradition of cooperation. So we formed in 2017 a company together with Vattenfall and LKAB, as said, to embark on a journey to see if we can take this from a laboratory scale into an industrial logic together, producing steel from using hydrogen instead of coal. It's supported by government. We have had funding support from the Swedish Energy Agency, and as said, the company was formed in 2017, and in the beginning of 2018, we took a decision to invest in a pilot plant, a big upscaling from laboratory. It's a 50-meter high building, actually, to test in a more upscale version of this process. Next picture, please. These 3 companies with the fossil-free mining, the fossil-free electricity, and the fossil-free steel gives a completely fossil-free value chain. So the logic is absolutely there. We are also 3 companies that have the same time horizon to be completely fossil free. So by 2045, we are all three committed to having on the market all of our products should be fossil free. So I think also in terms of utilizing more electricity for the process that we want to change, we need Vattenfall to contribute with the fossil-free electricity for it to make sense, and we need huge amounts. And we also need the iron ore to be prepared for that, to be able to be in this process. So it's a I think thinking about and talking about what makes laboratory findings and innovations fly. In this case, it is actually that we do this together, and these three companies is a match made in heaven. Next picture, please. And just again to visualize what we're doing, the production of fossil-free pellets is as LKAB will do, and they are embarking on that journey to be completely fossil-free by 2045. Production of fossil-free electricity, it's Vattenfall's goal to be completely fossil-free within 1 generation, is what they say. SSAB want to have a completely fossil-free production by 2045, and the hybrid initiative, that's a joint venture. We are now producing, actually, since May this year, fossil-free sponge iron. And we are also having a lot of, right now, partnerships with customers and users of fossil-free steel to learn together and also add in the value chain all the way to end user, actually. Next picture, please. So you also see the notes there. That's very good. So the aim of the hybrid initiative and the fact that that's behind all of this carbon dioxide emissions from steel industry is that the iron ore is a union between iron and oxygen. And in order to make steel, we need to remove the oxygen, and that has since the beginning been done with coal in a blast furnace with a lot of heat. The oxygen unions with the coal, and we get the iron to make steel from. In this new process, we replace the coal completely with hydrogen, making the byproduct instead of coal water. Next picture, please. And this is kind of the two routes of producing steel. With the gray is the current route for producing steel from iron ore, and the blast furnace. There exists also steel production from iron ore with natural gas, but in our system we use blast furnaces. And you can see that the carbon dioxide emission starts already in the pelletization when we take the iron ore and make pellets, and the pellets goes into the blast furnace, and that is where the chemical reaction happens. And actually 93% of SSAB's emissions today comes from the chemical reaction emissions in the blast furnace. And we look at the blue sky part of this picture, how we are thinking about the future system is that the pelletization is done with bio-oil, and we have a direct reduction shaft where we reduce the iron ore pellets using hydrogen. The hydrogen is produced in a fossil-free way. It is stored close to the plant, and we have a completely CO2-free system. When it comes to SSAB, to make steel from, we use an electric arc furnace equipment that is available actually today also, because that is the way we do steel from scrap. So that is not a new invention. So the new invention, the way of kind of taking this to a completely new level, that is what we're doing within the hybrid program. And you also have a timeline, 2016 to 17, we did the pre-feasibility study. Is this possible? Can this be done? We also did some energy energy studies, which you can see some numbers from the pre-feasibility study in the picture. We took a decision 2018, we need to scale this up. We need to look at how this chemical reaction and how this system works in a bigger scale than the lab. And 2018, we took a decision and we built a pilot plant. 2026, we aim to have a demonstration plant ready, and we are also changing and shutting down one of our first blast furnace in Oxelösund by 2026. So actually, that is the date where we will have our first delivery of fossil-free steel. Next picture. Again, it's the same picture or the same timeline written in another way. Lab scale gives us a good research base for how this process is working. What parameters can we see in the lab scale is needed. The pilot scale takes us to another level of industrialization, and we can take all of the findings that we have in the pilot scale phase now when we are starting actually to plan for our demonstration facility up in the north of Sweden. Next picture. I said collaboration is important, and the 3 companies doing this together is important, but we also have a lot of government support. And this is our Prime Minister at the inauguration of the world's first pilot plant for this hydrogen reduction process, taking it from laboratory testing towards a robust industry process. Next picture, please. The pilot project that we're running right now also includes, besides the hybrid, what all the 3 companies need to bring to the table in order to have a fossil-free product. We are looking at alternative heating techniques for sintering pellets. We're looking at the pellets production with bio-oil. We're looking at energy storage in caverns for hydrogen. Direct reduction, as said again in the hybrid project, and we as a steel making company need to learn how the pilot or the new process use the premium steels with the same characteristics as before. Next picture, please. Going back to our the official picture of the timeline and the development phases. The pilot plant trials will be running up until, as planned today, run up until 2024 in campaigns, and we are rebuilding and learning as we go further. The hydrogen storage is actually being inaugurated today. I met the press people at the airport. We are already planning for and engineering the demonstration plant that will be up. We will have erection started by 2023. We are, as said, continuously right now talking to customers of this fossil-free steel and planning for that in partnerships. Again, bringing in other industries to join us on this journey. And by 2026, we will close down the first blast furnace, and that is in Oxelösund. We will replace it with an arc furnace. The demonstration plant will give that arc furnace fossil-free material. Next picture, please. And as I said before, collaboration is key to success, I think, in a lot of areas. And in this, it really has. And we have found a very good support in each other, the 3 companies, in the universities, and also with the government. So I just want to give you end my presentation with a slideshow on some key moments also in what we're doing right now. So next picture, please. The hybrid pilot plant, we had a groundbreaking ceremony in June 2018 with the Swedish Prime Minister, all the 3 CEOs, and a lot of other people that wanted to join up in Luleå. Next picture. The pilot plant was finished and inaugurated in August 2020. Again, we had the Swedish Prime Minister, Stefan Löfven, present at the site when we did this inauguration. Next picture. In June this year, we had run our first successful 100% hydrogen reduced reduction in the pilot plant. And what you see in the picture is a bricketed HBI, fossil-free completely. And in that ceremony, we had the 3 CEOs. I think their commitment, the top management commitment, they've also been at all the different events we've had. Their commitment and their interest has also been a very good, or one of the key successes too, I think, with top management being so involved in what is happening and so interested. Maybe too much, some of the researchers have thought during the process. But I think it's been very important. Next picture. In August, we rolled the first steel plates in the world with this technology. And again, we had the 3 CEOs. We didn't have the Prime Minister, but we have the Swedish Minister for Enterprise at the site when we did this first. And these plates have been delivered to the first customer, which is Volvo AB in Sweden, and they will build a prototype using this material. That is the next step. Next picture. That's actually my end slide. This has been SSAB's vision since I started working for SSAB 2006, a stronger, lighter, a more sustainable world. And I really believe that this vision is known to everyone in the company. I think that whether you work with customers, we're also very specialized in high strengths and wear resistant steels. So whether you work with customers, you are constantly reminded of that we have a product that for our customers brings a stronger, light and more sustainable bird. If we work in our production, we've always been improving and trying always to be more and more sustainable in the production. That the vision works for everyone in the company, and I think that is also a part of us coming up with this challenge to the others. Can we do this? Let's do this, and that we're now doing this together. We're talking big investments here for all 3 companies. I think I stopped there. Open for questions.
Thank you, Eva, for your presentation of a very successful example of a research and innovation program, because this is a national program, very interesting, all the steps of this innovation process. There are many questions for you. From Mark Kozras. The premise is that carbon is an important element in steel. Has using hydrogen posed specific challenges to reintroducing carbon in the blast or electric arc furnace process steps?
It is absolutely part of the research that we're doing right now. What is the best process for introducing carbon in the steel, because it is an important part, and it needs to be done in another way than before. So that's absolutely part of the research that we're doing. I stopped there.
Okay. Yes, this is the disadvantage to having industrial contribution to the workshop. Okay, the other question is, did you receive a lot of public funding for this research and upscaling, or it is paid by the 3 companies?
We did get a lot of support, but we also invest a lot. The three companies. I would say for building the pilot plant, which is a very expensive venture, we got a little bit more from the government than we all three spent each. So the three companies did most of the investment, but if you divide it into four, the government did support us a little bit more than. But it really has been us four that's doing the investment, and it's a large investment. Absolutely. Mm.
Okay, from Calais. If you rely on intermittent electricity, you need the hydrogen production as buffer. What is the state of TRL for that? What is the power you need, and how large share of it is hydrogen production?
Oh, now you are asking questions that I the information is available, a lot of these numbers on our website for hybrid, but I can answer in general. Yes, wind power is intermittent, and yes, we need to store a lot of hydrogen, and that is actually part of when we did this energy or electricity study to see if this makes sense in industrialization, because we need a lot of hydrogen, and having also Vattenfall part of this project and doing research on storage. This will kind of be a buffer where we can actually save energy. We produce the hydrogen, we save the hydrogen, and we use it when we need it, so to speak. We don't have to have the production at the same time. So, and I think all the numbers on how much energy we need, it was on my slide, and it also is available on our website to look at. I think it's about 15 terawatts, but it depends on how much you include, and if you include, if you include the pelletization, if you and how there are numbers available, but yeah.
Another question from Fernando Oliveira. Hydrogen embrittlement of steel. It will not be an issue.
No, that is also something that, of course, is part of the research project, and being a producer of high strength steels and martensitic steels, for those who know steel materials, hydrogen embrittlement is something that we've been battling for decades. So we are really on top of that subject, making sure that hydrogen doesn't mess up the steel from the inside or from the outside. So that is a very active, I would say, research area for us, and has been for a long time.
General question that is very useful for us in terms of workshop organizer. How will the SAHAB's success impact the policy, the regulation on future steel industry at a wider national and international level?
I would say, trying to answer that question, it's a good question, and of course it's not a. Let me reason the answer. When we started to look at this in 2016, as said, in laboratory scale, that this could be done was already known, but to make it into an economical, cost-efficient industrial system, that's kind of the questions and the question that we asked ourselves when we started this, and when we started the pre-feasibility study, that was really part of it. How can we get fossil-free energy? How can we balance that with the cost for the system that we have today? How can we look at cost for emitting CO2? What are our prediction on how that will drive cost for making steel and such things? And we came to the conclusion that this needs to be done, And in Sweden, it makes perfect sense with these partners available, with the fossil-free electricity available, and so we embarked on this. And I think that many thought it was impossible to do, but I think that we have inspired others to now also look at this as a future possibility and look at what is needed in other parts of the world to make this happen, to kind of make sense in terms of all the things that is needed to make this happen. So we are part of a lot of conversations on EU level, of course, my co-worker Martin Pei, who is even closer to the hybrid initiative in the SSAB GEC, is now in Korea to talk about it. So we have a lot of attention and on this right now, and I think and I hope that we both influence and inspire others. That's what I think.
We have 2 minutes for questions. From Francesco Matteucci, do you think that it is possible to apply the design-driven innovation approach for your net zero steel?
Yes, in terms of looking at from the customer perspective, if that's what the question is about, I think yes, and that is really what I bring to the table and my background with the research that I've been doing before I started to work with SSAB and also within SSAB is always been about our customers utilizing our high strength steels and wear resistant steels, making sustainable products. As I said, we can use less steel to do the job. The steel has a longer lifespan, and so this is a way of working for us since long, and now to do it with a fossil-free steel and what is then for the end user or the consumer interesting, and we talked about feelings also before. I think that sustainable products has a feeling also, maybe not as an iPhone, it's another type of feeling, but that brings emotion, I think also, and who are interested in that, where does that do most use? That's approach, and that is approach that we have now with the customer collaborations that we're
therefore are you collaborating with the EU Green Steel Partnership?
Yes.
Sure.
The first call was closed last week or something like that, right?
Okay. And the last question is a technical question from Maximilian Wolf. How do you store the hydrogen? Are you using conventional pressure vessels? Are there plans for different technologies, and how is the technology readiness level, if so?
That is the Vattenfall's part, and as I said, part of the pilot is building a line rock cavern connected to the pilot plant up in Luleå, and that is inaugurated, I think, today or tomorrow. Maybe I'm saying too much now, but that is right now what we are doing, and Vattenfall is driving that part of the research. But that needs to, because we need to store a lot of hydrogen in the future, and that is not been done before. So that is also part of the research project. As said, we are connected to the pilots building an all LCR or LRC up in Luleå.
Thank you again, Eva, for your very, very interesting and your kindness in answering to all the questions. Thank you.
Thank you so much.
Okay, so I will take over from Monica for the last presentation today, after some reshuffling as we were obliged to do. So the last speaker is going to be Joachim Antonissen, who is the General Manager of Guaranteed. Joachim graduated in material science from Ghent University and holds right now several patents related to wire and arc additive manufacturing and development of high-strength steels. So please, Joachim, the floor is yours.
Okay, I hope you can hear me well.
Now, yes, we can hear you.
Okay. And are you seeing the presentation in full mode or in?
No, it's not in presentation mode. It's in...
Okay, let me see if I can modify this here.
Now we see it in, well, like before, in
yeah, I think
presenter mode.
Is it better now?
No, it's still the same.
Still the same? Okay.
I mean, we can see it, but
you have
we see
two
also
screens.
the next
We
one.
see the one with the small. Yeah, now it's.
Is it okay now or not?
Okay, now we can see it probably bigger than before, but it is not in presentation mode. That's the, it is in the normal mode when you edit the presentation.
Trying to do it like this then.
I think it depends on the screen. Ah, okay, now it's fine.
Now it's fine? Okay.
Yes,
good.
Yes.
So first of all, let me apologize also for the slight glitch in my agenda, but for some reason Outlook played a nasty trick on me by putting this in my agenda for tomorrow. So I actually had to reschedule a couple of meetings on short notice in order to be able to join you today. But that finally worked. So I'm happy to be here today and to present this presentation to you from the point of view of guarantees. So let me start by telling a small story, perhaps. So I think for all people who are working in a continuous production environment, you all recognize very well the picture on the left of this slide, this red button here, the emergency stop button, which is something you absolutely want to avoid hitting, because as soon as you do that, you basically have what is on the second picture in the middle of the slide, and you start burning money. Simply because your production line is stopped, you're losing productivity and you're losing money. Now, even if you don't push the emergency button, you're still losing money, you're still burning cash, for the simple reason that in order to avoid having to have a long standstill, you have typically to keep a lot of spare parts in stock just in case your line might fail. So even if that's not a direct cost, there is very often also an indirect cost, which is associated to the large spare parts and warehousings, which need to be taken care of. And it's exactly that what we are trying to solve with Guaranteed, by creating actually value for our customers by either remanufacturing, repairing, or refurbishing these large metal components which are used in this type of installations, in order to allow them to be operational all of the time, to allow them to extend the lifetime or prevent downtimes of that type of equipment. If I say we, it is the three shareholding companies that you see on the top of the slide. It's ArcelorMittal Belgium, which is part of the ArcelorMittal Group, which is worldwide largest steel producing company. We have OCAS, which is a research company based in Belgium, in the Flemish part of Belgium, which is specializing in metal-related research, and Finindus, which is a VC fund, a venture capital fund, which has a focus on investing into metal-related innovative industries or innovative ideas. Because of that shareholder structure, we also like to say that we are born from innovation, which we are using to guarantee to our customers a first-time right production. And at the same time, with link to our second shareholder, ArcelorMittal, we are also raised in industry, which we are using to guarantee also to our customers a one-stop shop and a reliable process. And I'll come back to both of these elements later on in the presentation as well. Now, as you can see, our mission of the company, it's value the future, upgrade the past. I already mentioned that we are focusing on remanufacturing, repairing, or refurbishing these type of installations in order to either prevent downtime or extend the lifetime of these type of components. That actually means that it's also very, very important to have a zero defect, high quality production capability. Because of course, if you're doing repair or remanufacturing, you only get one chance to get it right. And even when you're producing spare parts, as we are producing just in time rather than just in case, we also can't permit ourselves to have a long trial and error cycle. So that's why it's also very important for us to have a unique software capability that allows us to have that zero defect capability already from the design perspective, but also to have invested a lot of time and effort in putting in place a very advanced process monitoring capability in order to ensure also that what we are producing is actually conform to the specifications that we put on paper on beforehand. And finally, what the last element is that it's also very important for us to have a fully integrated production. So not just doing the actual 3D printing, but also doing all the required pre-processing and post-processing that might be required in order to have a full control over the quality and the lead time that we promise to our customers. Now let's make this a bit more tangible through a couple of examples just to frame the situation a bit clearer. This is an example of a wheel rim from a slab transporting vehicle which is used in the steel industry. There was a fatigue crack in one of these wheel rims, which was actually putting the vehicle out of use. And these are actually quite critical vehicles in the steel industry. If they're out of use, the entire downstream operations can be hindered by that. So they're quite essential. What we did is basically we removed the fatigue crack from the rim by grinding, and then we filled the groove that existed by new virgin material, which had the same properties than the original material. This resulted in a huge saving for the customer, as you can see on the slide. The new part would have costed around 60,000 euros, while the repair was only 5,000 euros. So there's a massive saving. But even more important, these wheel rims, they are used in Europe, but they actually are produced in the US. So they needed to be transported from the US to Europe, which has, of course, an ecological aspect, but also a lead time aspect, while the repair only took 2 to 3 days to be completely completed. We also performed a lifecycle analysis on this case, where we compared the original conventional manufacturing method of casting and forging for these type of components to the WAM repair option. And you can see on the picture on the left of the slide that this actually results in a huge saving for the customer in terms of carbon emissions, which are then secondary or tertiary emissions, which can be taken into account also in a green steel initiative, for instance. Second example is this broken mandrel bushing that we refurbished. Again, you see on the top of the slide the different steps which are being taken. So we start from the original defect, we remove that defect, we fill it with new material, and we do the final machining to bring it back to the correct dimensional tolerances so that the part can be used again once it leaves our production line. Now, in this case, actually also a very nice example to illustrate what we can do in terms of refurbishment, in terms of upgrading, because actually, if you compare the original material that was used to produce this part to the new material which we deposited, the new material has a tensile strength which is about 15% higher than the original part, which actually means that the lifetime after repair will be longer than the original part. So again, besides the pure cost savings that resulted from producing this or repairing this part instead of buying a new one, there will also be secondary savings that can be realized later on, which are related to the increased lifetime of the component. And the last example, just to illustrate the story a bit more, is impellers, diffusers, which are of course also very often used in industry, where we're working both on the production of completely new ones, for instance, to replace obsoleted parts, but again, also on the option of repairing those. You see an example here of a stainless steel impeller, which we refurbished, where again, the savings were about 40–50% as compared to buying the original new part. Now, as I mentioned, as we are born from innovation, we also like to take this a couple of steps further by working on a couple of new technologies in order to enhance further the quality, the performance of the parts that we repair or that we produce. And I'll give a couple of examples on how we use also results from innovation in our actual production. This is a first example. As you know, additive manufacturing, especially for alloys like titanium or aluminium, can result in an elongated grain due to the solidification scheme of these type of materials. What we are currently doing is we're working in a European project on a way to actually lead to grain refinement directly on the as deposited microstructure, so that we can avoid having to go through a thermal cycle after production, which of course leads again to significant cost savings for the end user. We're doing that in a couple of different ways. On the one hand, by introducing some kind of mechanical work directly during the actual solidification, by introducing also inoculants into the material so that we can get nucleation going, and with those technologies, we also have the ability to close any residual porosity that might still be present in the alloy once it's being deposited. So this is a first new innovative technology, which we will be introducing into the market probably in the course of next year. Second example of how we're using innovation, it's in our process monitoring. This is an example of what we're doing in order to ensure, because a lot of our customers are, of course, using these parts in highly critical applications, so they need to be qualified, they need to be certified. So what we have implemented is a way to monitor all relevant production parameters and to actually plot them on the deposition trajectory of our robot, so that we can get a full digital fingerprint of the part once it's being produced, which can then be used in a qualification or a certification scheme in order to have, let's say, the process qualification and the part qualification being done in the most efficient manner. Another example is our software, where we're having a full digital twin of our actual process software. So on the one hand, the process software itself is creating, of course, the deposition trajectories for the robots in order to do the wire and arc additive manufacturing process, which is the main process which we're using, which is already having a lot of intelligence embedded directly into that software, because we're actually using experimental work that was done in the past in order to directly introduce also the right process settings into our software. But at the same time, we developed a full digital twin where we're actually taking the deposition path and putting it through the digital twin in order to ensure that the part which is being produced in this way has the right mechanical properties, has the right performance, is fit for purpose. And I'll explain in the next couple of slides a bit more in detail what exactly we're doing in that respect. So of course, the first step is to understand, if we're running our process, what is the heat which we're putting into the material. And for that, we developed a full weld pool modeling software solution, which you see here on the slide, where we're basically using the composition of the filler material and the base material as a way, and as well as the process conditions, in order to predict what is the local and transient composition, temperature, and geometry of the weld bead. So this way we get a full picture on the one hand, the geometry of the bead, but also on its composition, as well as on the transient heat behavior of the component. A couple of examples on how we validated that. So you see on the right hand of the picture the actual micrograph of the bead on plate test that we've done. On the left, you see the simulation results, and you directly see that they actually match very closely. This gives us confidence that we're actually capable of predicting the beads in the correct way. We're using that now to generate process maps, where, for instance, you see here that we're looking at what is the impact of variations in torch speed, wire feed speed on, for instance, the bead width and the bead height, because these are, of course, essential parameters in order to ensure that we respect the right geometry of the part that needs to be printed. We're also using it to look at what is the impact of these process conditions on the bead overlapping, because of course you can produce single bead walls, but in most cases we're actually producing massive components. So we have several beads next to each other, and then we want to have an as smooth surface as possible in order to have a nice surface appearance. So we're using also these type of models in order to understand what is the impact of the process conditions on the smoothness of that surface that we're generating. And last but not least, we're also using it, of course, to look at what is the impact of the process conditions on the thermal fields. So you see an illustration here where we're actually plotting that transient behavior in a few points in the weld bead for different process conditions, to understand how are the process conditions actually going to influence the thermal behavior of the part, which is of course essential if you want to control things like distortion or warping of the component, but also if you want to control the microstructure, which is actually the next step that I'm showing on this slide, where we developed a full microstructural weld modeling capability as well, where we're predicting on the one hand the local CCT curves based on the local composition, and then we're predicting what type of phase transformations are happening in the material, which then in turn will lead to the warping or the distortion, and where we can then predict between different potential deposition trajectories, which would be the most optimal trajectory in order to avoid distortion altogether. And last element in that chain of simulation is then to understand if we're now taking that predicted microstructure and we're loading it with the real life loading conditions that the components actually also going to see in real life, how is then the part going to behave? And this is done by creating a representative volume element and submitting it to a crystal plasticity model in order to understand how is that microstructure going to respond to the actual use case, to the actual loading conditions, and then to optimize that entire chain. At the moment, we're involved in a project where we're actually going to do the opposite direction of that chain to actually try to produce the ideal microstructure for a given load case. And this is something which we're doing on the one hand using neural networks, and on the other hand also coming to a full inverse coupling process structure, microstructure relationships, where we're then should be able in 1 or 2 years from now to really predict what would be the optimal process conditions which give rise to the optimal microstructure, which lead to an optimal behavior of those type of components. This is all brought together in Guaranteed in our DNA, where we're bringing together on the one hand the industrial footprint of our shareholders in order to ensure that we have a very robust way of operation, a very well organized way of operating, but on the other hand also bringing the innovative elements from our second shareholder, which is OCAS, the research company, in order to ensure that we're at the top edge of what innovation brings in this field, in order to together guarantee the quality of the parts that we are delivering to our customers. Because as I mentioned, very often they're actually using these components in safety critical applications. So it's very, very important that the quality of these parts can be assured. At the moment, we have a production facility which is located in Ghent, in Belgium, which is fully operational, which has unique capabilities in terms of dimensions. As you see on the slide, we have possibility to produce parts up to 10 by 6 by 5 meters, and we're able to manipulate components up to a total weight of 20 tons. And we're doing that for a variety of different materials, from carbon steel, stainless steels, nickel-based alloys, aluminium and titanium, because we're using also different welding processes in our operations. In the future, what we're adding as well, it's in situ non-destructive testing, because we believe that it's very important, as we're aiming for large structures, to already be able to do that type of inspection during the actual process. On the one hand, to ensure that we interrupt the process if there would be a failure, that we can stop as soon as possible, but also again to avoid having to do that type of non-destructive testing on large components a posteriori, because again that would drive up the cost and lead to a negative business case. That brings me to the last slide in my presentation, which is basically summarizing the main benefits that Guaranteed is bringing to this large-scale additive manufacturing field, which is on the one hand that we're offering a very cost-efficient technology because we're using this wire and arc additive manufacturing. We have unique dimensional capabilities that I mentioned before of 10 by 6 by 5 meters. We're able not just to produce new parts, but also to repair parts, which allows us to bring an answer to obsolescence management, for instance. We're at the same time able to optimize the performance of the components. And through our unique software, we're also able to provide a guarantee on the performance of these parts. And bringing all that together then helps our customers to realize a sustainable and eco-friendly approach to spare part management, with the resulting also reduction in logistic costs, because you can reduce the amount of spare parts and at the same time reduce the lead times. This is now fully operational, and we're always very interested to work with a lot of different companies, a lot of different challenges, because we're also convinced that this is actually going to help us move forward in a more efficient manner. This was basically what I wanted to bring today for today's webinar, and I'll be happy to take any questions during the Q&A session.
Thank you very much, Joachim. It was actually extremely interesting, and also, in fact, involving several aspects, from the actual manufacturing to the modeling to the non-destructive examination. So I think it's really extremely fascinating. So I think there are questions. Monica, will you deal with that if you wish?
Yes, sure. The first question for Joachim is, about the testing. What kind of tests do you do after repairs? Anthony, assume hydrostatic test and a positive material inspection, fluorescence, I think so.
Oh, well, it actually depends a little bit on the qualification requirements for the parts. So for instance, if I give the example of the oil and gas or maritime sector, where the first guidelines are now being developed, basically what has been done, there has been different categories of parts that have been defined, different criticality levels, so criticality level 1 up to 3, where depending on the criticality level, the build process qualification, which needs to be done before you're actually producing a part, will have different requirements in terms of testing. So if you look at the most advanced type of category of parts, which is the criticality level number 3, then this involves doing tensile tests, Sharpie tests, bend tests, metallography, porosity measurement on the build process qualification. And then this is basically being locked. And once you then go into production and you're using that type of validated process, then you do a repetitive production testing in which you do a narrowed down scope of testing in order to prove that what you're actually producing is consistent with what has been validated during the build process qualification.
Second question is from Kali. He finds what you do quite fascinating, really applied research and development. Kali assumes you collaborated with universities and research centers. How is that organized? How much of the work is done in-house directly and how much by partners?
No, it's indeed a very good question. Indeed, there was a lot of collaboration that was done prior to the startup of the company, actually. And even now, still during the initial years that we are operating, we're still having a lot of collaborations. I think it's essential for the startup to remain in collaboration with universities, because I think this allows to be at the forefront of the technology. At the same time, it's also essential, I think, at the startup phase itself, in order to ensure that the technologies which you're actually bringing into production, that these are sufficiently mature. So that's what I meant, that we had worked with universities before launching the company. And then the offer that we're basically integrating at that phase was mature. And now we're still collaborating with universities, but this is for technology that we will be introducing in 1 or 2 or 3 years from now in order to prepare the future.
The last question is for Mark Kozras. Your technique is of significant interest in a material acceleration platform implementation. See the question previously posed to Tommy. His mention of implementing a MIP on a synchrotron may be highly relevant to advise your models and material development.
Yep.
What do you think about?
No, it's something which I think it is for sure relevant. We are thinking also of ways of accelerating the generation of or the implementation of new materials to come up with kind of standard workflows where we produce kind of standardized test samples, which can then be qualified also or characterized in a standardized way, in order to populate a database that can directly be plugged into our process software. So this is something we are very much interested in, because we do get requests for new materials which are not yet in our database. The database is already quite well populated. I think there's something like close to 25 or 28 different materials already inside. But still, we see that every day we get requests for materials which are not yet in that list. So it's for sure a relevant aspect.
Okay, and I have a question about the validation process for specific sectors like aerospatial, space, aerospace, aeronautics, and so on. This technique are quite difficult to be accepted in these sectors. How can you, in some way, push this this new way?
think if you look within the wide range of different additive manufacturing technologies, we are probably in a favorable position using wire arc additive manufacturing, because it actually is very, very close to welding. The basic technologies which we're using are welding technologies. We're highly automating them and we're putting some more intelligence in it. But in the end, it's still a welding process. And these have, of course, already been validated in a lot of different industries, amongst which also aerospace. So that's at least the feedback that we're also getting from the people in aerospace that we're working with, that this is for them probably the AM technology which is easiest to validate, which doesn't mean it's easy as such. Yeah, I think that the different steps that we see is that in the short term, it will still require quite a lot of physical non-destructive, destructive testing, sorry. In the longer term, I think we will be able to use more and more process monitoring, because this is, of course, one of the advantages that these new technologies brings, that they are highly monitored. And we should be able to use more and more process monitoring as a substitute to physical testing, putting then also some machine learning and AI into that equation in order to detect anomalies in the process monitoring and correlating them to defects that were detected using conventional testing.
Thank you, Joachim. I don't see any other questions in the chat, therefore, thank you again for your presentation.
Yes, and indeed, I think that we should, we have 15 minutes of delay with respect to the planned timing. I think that we can shift everything rigidly by 15 minutes if everyone agrees, so that we have, let's say, the expected time for the panel discussion. And I see Holger is ready to take the lead, so please, Holger, it's your moment.
Thank you, Lorenzo. Today I can welcome in the panel Joachim. Joachim, could you please turn on your camera again? Yeah, right. Mark Kodrash, Stefano Martinucci, and Alicia Main. Stefano, Francesco Martinucci, he is in, he was working for the IC, a 20 years researcher, with his background of 20 years research, and he's now trying to boost innovation. Alicia Main, she's working for the Simon Fraser University in Vancouver, and during her whole career, innovation was one of key focus areas. And finally, we have Mark Kodrash. He is a co-lead of the Mission Innovation Platform Materials for Innovation. And I think these four will give us deep insights and will help us to extract the most important issues for innovation. Finally, I would like to say here in the introduction that the audience could please also send questions to the chat, and in the last 10 minutes we will try to use to extract a few of them, and then you basically have the possibility to raise these questions to our experts. And I will also start with a teaser, so to speak. I think the energy field, the energy research field, is a very special one, because the market is very much related to taxations and to subsidies which are on top of it. For example, in the car industry, most of the innovations are coming from industries, where in the energy field, for example, materials are generated and produced by, often by research organizations. And we have seen this yesterday, the track from first research results to the market is about 20 years, which is a very, very long time. The stable conditions for industries are often changing. For example, the feed-in tariffs where came up and they dropped. And this is, of course, not good for the industries to do research. How could we change this to bring the innovation to industry again? And the other way, we could attack this issue is we simply speed up innovation. What kind of forms could be used to really brings this 20 years of innovation down to 2 years. And I would like to start, also please extract the key issues for innovation. And Francesco, what is your opinion here?
Yeah, I think that to boost from 20 to 2, it's quite ambitious. You know, I spent last night having a very nice reading of Alicia paper on nature materials, and listening also, I mean, studying the materials on mission innovation, just to try to give a reasonable answer to the terrible question I knew that you would have, Olga would have done me. And so just to start from the end, I think that at least to boost, I don't know if for 10.4 or 1.54, I think that as Roberto told us, the management, the organization, you know, put in place all the steps, make, you know, what it's called to be easy, but it's not so easy to put the right resources to reach the right deliverables. And resources in the end are always money and people. Obviously, okay, you can put infrastructure, whatever you want, but if you've got the money, the people, I mean, you are not in the worst position. So I would say that the management is a good departure. Then obviously, Olga, if we are speaking about materials, we have seen that all the projects, all the scale up that has been shown in these two are really interesting, and congratulations to all of you for the interesting talks that were taken. I feel that we have seen that we are in a field, materials for energy or materials in general, where we really need an open approach. That means working not only inside your organization, but being open to share the knowledge outside. We have also seen that it's not an issue, the IP. If you manage it properly, you can manage the right IP. So just to give the floor to the other speakers, I would say that if you start with the right organization and with an open innovation approach, I feel that your success rate increases and your speed as well. And I would simply say that not always science at a certain point has to be the driving force of the material scale up. And this is part, once again, of the team. If we leave, you know, today I was, I cannot say why, but I was involved in a meeting for new employment inside European Commission. It was the first time because I'm brand new. And they discussed a lot on looking, for example, on who should be in the selection committee of people. If we put in the selection committee of people only the researcher or scientist, we will get out wonderful new employees, but science-based. So also this merge in the people identification, it's crucial. I shut up.
Okay. Alicia, what do you think?
Yeah, I agree with Francesco. Am I saying your name correctly? Yeah, on most of the things that he just said. And certainly I think the 2-year plan is a bit too ambitious for some of the important clean energy transition inventions that we need to get in the world, just the scale of proving them technically and scale up, but a good target to have, maybe 5 years instead of 20 years is what I would aim for. And where I would build on what Francesco just told us is, I would say you need the people, but you also need the people that have the right mix of interdisciplinary capabilities. And so if you just have the technical people and the business people, both of whom you need, you're not going to recognize or create the full range of opportunities to be able to effectively commercialize breakthrough invention. And so it's having languages, common languages in your organization where the technical and business people can co-create opportunities. And so that brings back to the talk that I gave yesterday about that key capability of technology market matching, how it needs to start in the research lab. That's usually before you have business people involved. And so it is this iterative process of prioritizing technology attributes to develop further, and market applications and indeed market segments to pursue, that needs to start with the scientist. And so that means that, although I fully agree that our selection panels and whatnot should not be full of highly expert, narrowly educated scientist, I would say that the scientists' views are essential in this field, and they need to be complemented. And so whether that can be in the same individual with the dual lens, that's something that I would advocate for. And again, because to shorten this process, we have to start earlier back, and it has to be an iterative strategic approach.
Okay, this was complicated for me, a complicated answer.
Well, actually, I do think that it's about entrepreneurial capabilities and mindset in scientists is a big piece of that key to allow them to do these things that we're asking to happen.
Okay. Joachim, what's your opinion here?
Oh, I would add to that I think what's also very, very important is to listen really very, very closely to your customers and try to really understand what are the problems that they are facing, and to bring a first solution to the first problem, and don't try to aim for only bringing the solution to the market once you have solved all problems of the world, because I think that's typically a pitfall that a lot of people go into, that you try to develop something which has all the features already included from day one. I think it's good to try to develop something which is mature and then bring that to the market, but which has perhaps 80% of what you need, but not the full 100%. And that will already be answering to the big needs of your customers, and they will be much more happy that you can bring that indeed in 2 years than in 20 years, the 100%. And so I think that's a critical message from my side. And linked to that, I think in terms of the complementary of the team, I think you do indeed need to have people on board in your startup as well, who are in love with the customer, with the market, rather than in love with the technology. I think this is a bit hand in hand with what I just said before. This actually helps you to really focus on the customer needs rather than on the technology itself. And I think this is the second pitfall that I see a lot of companies going into, that you're so much in love with the technology that you just want to keep developing and developing, and you actually don't want really to put it on the market, because then the development stops. So I think these are for me the two complementary remarks that I wanted to make. I have to apologize because I also will need to disconnect, because I actually have a meeting with the customer that I needed to postpone. So my apologies, I'll need to leave.
Okay, thank you, Joachim.
Thank you.
I have to challenge you now. The maps claim to reduce the innovation time by a factor of 10. But what I've heard is that technology is not all of it, and the maps are mainly technology related. So where do we get the entrepreneurship, the market space into the mission innovation activities?
Oh, Holger, that's a very good question. I've spent 4 years identifying what a map is, first of all, and then trying to realize it and its benefits. So when we challenged ourselves in 2017 to accelerate materials development by a factor of 10, at least 10, so taking 20 to 2 years, that was notional. It was a stretch goal. Of course, we challenged ourselves aggressively. But what we've done in the last 3 to 4 years is demonstrated that there are aspects of the developments that we can accelerate. For instance, we improved, the broad global team was able to use 1/34th of the amount of precious metals or expensive materials in experimentation. Okay, if they can reduce their use of, let's call it platinum, and by a factor of 34, and they can do 100 more experiments than they would have, that acceleration alone, that's one factor of acceleration. If we can put out 20 experiments in a day when conventional science methods put out 2 in a month, that acceleration is what we're demonstrating today. So will we achieve a 20 to 2? change? No. Will we achieve a 20-5? Alicia, I believe we will. And Francesco, we did challenge ourselves aggressively. We had to, because this is a huge problem. It's a huge global problem. And so MAPS is there to help us realize whether we can do it or not, the initiative. So if we don't, I guess, continue focusing, Holger, we will never get there with materials. Materials make up 50 to 80% of clean energy costs. Okay, so we know that we need that. Now I'm going to jump back because there's a bunch of statements that I really loved. We need specialists, but we need generalists. I'm paraphrasing a bit. We need border people. We learned that in one of the presentations today. We need to start earlier. Thank you, Alicia, for reiterating that just now. We need the voice of the customer, Joachim. He just stated it very clearly. And we don't have to be perfect. Okay, now we've set the parameters for all this multidisciplinary team. And how do we achieve it? We think of those constraints parameters, the box that we're working within, and we move forward as best we can with focused resources. And Francesco clearly stated, they're dollars and people. And I'll leave it at that.
Okay, thanks, Mark. I have another question to Francesco. I mean, if we generate new materials, higher performing materials, and maybe there are no problems with critical raw materials, but we introduce materials which are not accepted by regulations, yeah, because they were simply forgotten or whatever. How can we push to change the regulations for these new technologies? I mean, to bring them in the market.
Yeah, I can give you one good example and one bad example. The bad example has been my unsuccess. I was managing and I was a co-founder of a company developing third generation photovoltaics. And I am still strongly convinced that the problem for this kind of technology is exactly what you said. That means the certification of the product. The market is selling first and second generation photovoltaics with all the lobbies behind, without considering what Mark said now, what Elisa said, that are the prioritizing product requirements. You know, nobody has never thought that, I mean, you can sell, if you want to put, just to make a stupid example, if you want to put a cell on my mobile, it doesn't need to work for 20 years, because in 2 years, my kid will destroy my mobile, okay? And I was not able, and after 7 years of work in this startup, we bankrupted. And now it was 2007, now we are 2021, and I've been invited by a colleague from JRC to put in place, a procedure to start looking for the different certification of this kind of technology. It is only 15 years. So that's not the good news. And I see if it will start in November. So just to make and it has been a case, I've been called there only because one of the PhD the students I managed, she's there and she told, oh, you have to call Francesco, you might know something about it. And that's the bad news. The good news is not so good, but European Commission put in place, Holger, I don't know, because it's not so common, the thing I will say, it is not a new tool, it is an old tool, but thanks to President Ursula von der Leyen and to the Commissioner, Gabriel, they want to repush it. It's called Innovation Deal. And it's when stakeholders group together and ask to the European Commission to put an accent on a topic that is an innovation barrier from the normative, regulatory, or certification point of view. When I say to put the accent, means one thing that when I was out of European Commission, I would say, no, it's impossible. Is it so difficult? Yes, it is so difficult. It is to put in place an inter-service group of European Commission. That means to sit around the table, all the relevant DGs working on this topic. DGs, you know, are ministries compared to Canada or US. So all the relevant European ministries, the director, in front of a table where the stakeholder comes and say, hey, guys, that's the innovation. You paid me for the development of innovation. but there is a market barrier due to legislation. And so the good and bad news is that I'm trying with my colleague Marco to push on one innovation deal. We try to push the stakeholders because we think, and they appreciate it, but from the other side, European Commission doesn't want to work on it because they say, no, it's not such a barrier. So it's not so easy to put this process in place. But just to give you, Holger, one example that the mentality of the open approach to put the people, colleagues of European Commission around the same table can be something that for Europe could partially change, because then I shut up. The final aim of this innovation deal is to write something that is a recommendation for policymakers. That means it's a document that European Commission will send to European Parliament and to all the member states ministries saying, hey guys, that's the situation. And that's, in my idea, we should discuss it seriously. I know it's not a very incredible step, but it's what I know that it started a few weeks ago.
I think this is great. This is really good news because at least, I mean, I'm in Brussels in 20 years, but I mean, this was one of the problems I never had an attachment to. Yeah.
Yeah.
Mark, do you have other ideas what could hamper innovation?
Yeah, and I'll just quickly state that I think Alicia and I were nodding a great deal during Francesco's comments on the policy document, because policy helps to inform. When we start creating information that the policymakers can digest, it allows regulation to be influenced and move in time. And some of the ideas Francesco just presented are great ideas for that. I'll say that some discussion yesterday around the actual supply chain, the value chain, is critically important to this, and how we integrate and understand the different facets of the marketing and the generalist and the expert scientist and everything. So that value chain for materials needs to be really understood to move forward. And then it impacts back on, because we understand the value chain, it impacts back on what resources do we have? What are we actually looking at in terms of material resources? What are the things that we're starting from? How do we pull that in through a structured approach and do some of this prioritization that Francesco talked about on the product evolution? Do some of the accent on the barriers, not only to the policy and regulation, but back to the materials barriers and gaps that the scientists like to address so aggressively. So I want to kind of loop in the idea of the supplier value chain and make sure that we're also realizing that we rely a great deal on the natural resources that we come from. I come from Natural Resources Canada. It's a natural thing for me to think about. Thanks, Holger.
Alicia, what are the main bottlenecks? What's your for innovation?
Yes, well, thank you. Thank you, Holger. I'd like to build, I'd like to agree with the comments made by both Francesco and Mark and build on them. I would say that the regulatory challenge is very real. And I'm heartened by the approach that Francesco and his colleagues are taking, and that is being taken in Europe. My perspective is that from the scientist and from the venture, the choice that you have is which of the market applications and segments, when often you have a number of choices with whatever materials, novel materials invention that you've created, which one do you prioritize first? Because that regulatory challenge, you can see it in advance. And so when you're making your commercialization strategy, when you're in the lab, when you're thinking about which technology attributes to be prioritizing and which of these novel materials to be incorporating, etc., and how much of each attribute to be giving, what's the balance? It's a multi-attribute trade-off decision, optimization decision, right? But it's also that market selection and prioritization. And I'm not saying that you only pick one market. I'm saying that you identify this regulatory challenge, and you actually a really good tool to use is where to play. If people aren't familiar with it, Mark Gruber and Sharon Tal Mark's at EPFL Lausanne, and has written a great book that is as a systematic way to help you go through these potential market applications at a very early stage. By doing so, you may be strategically developing IP on some of the markets that do have regulatory challenges, but you're trying to get to market, usually to the point that Joachim made, a drop-in application, an application that is not utilizing all of your technology. It's using, to his point, maybe 8% of it, but in something where you can prove the commercial ability and where you can start generating revenue, because that's going to change the game for you. It's going to change the game both in terms of resources that you're bringing into your company. It's also going to change it in terms of credibility with investors, with alliance partners, and with regulatory bodies. So you're going to be asked to sit on those panels for emerging markets once you have a market application that's been adopted. So again, I would say that early stage technology market matching includes looking at regulatory challenges and then actively hoping to change them. The second thing I would say for policy, for both for the bottlenecks and policy approaches to change them, I've been talking a lot with policymakers regionally and nationally about build for scale strategies. So there's a lot of talk about scale ups and about scaling up companies. In Canada, we have a lot of SMEs, and we would like to have more large multinational companies. But in this space, I think an overlooked component is building for scale with your innovation policy. And again, starting very early within the research institutes and the labs. And some of the small bets and policy bets that can be made are about allowing for IP strategy and commercialization strategy, allowing for this interdisciplinary mindset and actually nurturing this interdisciplinary mindset in postdoctoral fellows and in STEM graduate students and faculty for that matter. And then de-risking, allowing for existing facilities in government research labs and universities to be used for de-risking technology inventions, but systematically. So I don't want to take any more time at this point, but I can put in the post an op-ed that I've written on that, on a build for scale strategy that is very applicable to advancing and speeding up materials research for energy applications.
Okay, I mean, your comments basically raised the question to Francesco for me. We have a special organ now in the European Commission for Innovation, the EIC. And I mean, our greatest problem, or at least for me, is the climate change in the future. And indeed, we have now this Pathfinder call for green hydrogen. And this is great because it's especially focused on new technologies for hydrogen. But hydrogen will be the vector in the future for the energy system. So, I mean, how could we educate more people looking into this area? I mean, could we have, for example, special Marie Curie actions to set up networks, coordination activities for hydrogen research? And could we couple those activities with background from entrepreneurship so that the people are educated to really also to transfer their knowledge into the industry? So, I mean, this could be of interest for the EIC. Or you have to unmute your...
I was fighting because I went to the link sent by Elisha and it disappeared everything else from my laptop. So, you know, I was fighting. Yeah, just first, I'm happy to know that you read our proposal because it has been the first job I did with the money you are paying me inside EIC to write together with Marco the proposal. And to answer you formally, I feel that there are some actions. It's on top of clean hydrogen partnership to take care of the dissemination actions, the old JTI FCH with which we collaborate. You all know that FCH has got how they call it, co-programmed partnership. That means half of the budget is given by companies and half of the budget is given by European Commission. They do their own work program. In the other laptop, I'm now looking at the corrections potential of their work program, as well as they corrected our work program. So that's the good news. So concerning what you said on communication, yeah, I feel that it's necessary to do it. There is a long job to be done. Not yet, in my opinion, really done with the population. I hope you are not completely right when you say that hydrogen will be the only energy vector, because I feel also that ammonia, ethanol, methanol, and other CHN, organic chemistry materials. Unfortunately, I'm ignorant of organic chemistry. I did only one exam 25 years ago. I always work with inorganic, but I feel there will be other carriers of energy carriers. But in the side of hydrogen, I can only say that from the industrial point of view, colleagues, I feel that the acknowledgement on the importance, on the potential opportunities, but also problems of hydrogen is going on. There is a strong, in my opinion, effort we all have to do to work on the topic. That's my personal. I'm not speaking for the European Commission. I'm speaking for Francesco Matteucci. You know, we always have to say this. They obliged us. So in my opinion, we should a lot focus more on renewable hydrogen. And I don't feel that the blue hydrogen is the solution. And I don't think that it will be the solution and not also the solution in between. That's my personal point of view. I don't want to say this, but I feel that is an agreement between someone that doesn't want to change and someone that say, okay, we can also delay the change. I don't think we can delay. We have to do it now. And so the acknowledgement is necessary. And just to close, I feel that the multidisciplinary approach of the Marie Curie that you said, Olga, are crucial. We are trying with some colleagues of yours, some scientists as all you, working to combine the EIC with Marie Curie. It's a topic. We only had two meetings. The second one will be the 11th of October. And the idea here is exactly to put also, you know, a different point of view when saying I communicate a potential opportunity for hydrogen. We all know that psychologists created the syndrome on hydrogen use due to the famous problem. And so there is a lot to be done. But there is already what I feel that is quite strange, in my humble opinion, is that there are already lobbies inside how to develop the whole value chain of hydrogen. We all know that hydrogen economy is done of different steps. Once you change the vector, the storage material, the compressor, you go in one way. If you do not change, you go another way. But there is a lot of know-how. Just to close, I don't know if you know, but I'm sure some of you knows that how you call the B-52, the boats that goes under the water. I don't know in US how you say submersible. No.
Submarine?
Submarine, yes. There are submarines in 2 countries that are already going with hydrogen, and inside the chamber, sorry, not inside, outside of the chamber, there are more than 150 tons of metal hydrates, storing the hydrogen and give it to the fuel cell inside the submarines. And I was working on this on 2007. I mean, it was already in the sea, and I was working trying to provide them renewable hydrogen. Okay, so it was 2007. My hair was not so white. And this means that there is a lot to be done on both sides, to shut up then, on the communication side, but also on the capability of sharing once again the know-how.
What is, Mark, what is in Canada ongoing with on hydrogen research and bringing it to innovation?
The hydrogen focus is still being developed as the strategy within the government. So they're at the stage now where they've looked at it. They're creating the strategy to move forward. I would say that as things evolve globally, we'll get a better understanding of the role that we will play with hydrogen. Let's face it, there's a lot of clean electricity generation in Canada that can be utilized for this. There's other pathways, as Francesco mentioned, around the different types of hydrogen that will remain a priority because of the nature of what Canada's natural resources are. And so I actually made a note that it's a regional thing. We have to look at this as a global problem, but it's a regional decision that has to look at what the phasing, the timing of different transitions will be. Francesco probably has made good comments, and I'm speaking for myself as well, but Francesco has made some good comments that the end vector may need to be focused on of the green approach. But in between, we'll have some transitionary activity. And so we have to recognize that, and we have to recognize the geography of that, the regionality of that moving forward. So I would say that we are establishing it, but we are also setting up to, I guess, attack the hydrogen problem in as an aggressive way as we can from a scientific perspective. MAPS is being deployed. MAPS are being deployed right now to prepare us for that kind of activity. So we're starting in Canada is what I would say.
Okay. Alicia, you also have a contribution to hydrogen?
Yes, thank you. Excellent points made by my fellow panelists. I would say I look at the clean energy transition in two phases. One, like a lot of the technology roadmaps, the International Energy Agency map, the Canadian Hydrogen Strategy map. But I look at the time from now to 2030 as an adoption phase, and there's lots of low-hanging fruit that we have right now that can be done with incentives to companies that exist currently. And then 2030 to 2050 as, I'm calling it a discovery phase only because that's the stage that those technologies, many of them are in right now. And there are things that we have to do to that discovery phase now to make them into adoption phase by 2030. And so that's the part that I focus on. The things that are in research labs right now. So the International Energy Agency tells us that they believe that 50% of the technologies that we need to meet our net zero commitments in 2050 are, either not discovered or in the research lab. And what can we do to get them out of the lab and into adoption ready technologies? And that includes all the green energy technologies, the green hydrogen technologies, and also, better carbon capture and storage technologies. We have pieces now, but there are many pieces we don't have good solutions for yet. And I'm thinking of the emissions intensive trade exposed industries and being able to use green hydrogen for them where it makes sense. And so those are tough innovation policy and climate policy challenges, and there are also materials innovation challenges. So my message here would be not so much that we have to choose green or blue hydrogen, but not if we in Canada, the reality is there probably will be blue for a certain period of time, and not to lock out green while doing that, to be really purposeful with how we build the sectors, how we look at that technology market matching, but also we look purposefully at procurement policies and at the climate policies that we use to make sure that transition happens as the technologies are ready.
Okay, thank you. Lorenzo, are there questions from the audience to the panelists? Maybe he's not in.
Yeah, I have to unmute myself. And not that I can see, actually. I don't see any questions from the audience at the moment.
Okay. So then we can make a final round, final conclusions, or as an alternative, we had hydrogen as one of the key factors. There's another one we discussed a lot about functional materials, and we also discussed about steels. And steels is, of course, also, I mean, it's the production of steels. It's also just, for example, for the use of in nuclear power plants, or as to get steels better in geothermal applications. How could we basically connect? I mean, this whole workshop series is about connecting different research fields. For example, the geothermal people with the nuclear people. How could we bring them together? What kind of programs? It is just research related in the moment. The researchers meet, and the knowledge needs to be transferred. This is what I've learned immediately. So we have to establish new groups, and somehow we have also to bring in entrepreneurships. How, I mean, this is done in the next phase after, yeah, Alicia.
So one suggestion that I have is to think about integrating those objectives into some sort of training program. And so one thing that we've done in Canada in partnership with MyTax, which is a nonprofit that brings industry and academia together. It's funded by the Canadian federal government and through regional governments, and also has industry matching funds. We've partnered with them in developing innovation skills training for STEM scientists and engineers. And that crosses many sectors, but then you purposefully group them. And they look at their learning innovation skills and entrepreneurial mindset together, and applying it every module. A lot of this is asynchronous learning. They're applying it to their innovation idea, their commercialization idea. But what's happening and what we're watching happen is that there's a culture building, there's a common language building. And when people are commenting on the commercialization strategy of their colleagues' ideas, they're learning a lot about, and at the level, they're learning a lot about each other's technology objectives at the level of something where you can span disciplines. So, an unexpected benefit was that sort of collaboration happening across the cohort that, steps outside of the skills training itself and leads to common initiatives. So perhaps some sort of purposely designed training program where you're trying to do a number of those things at once with cohorts of scientists that you want to take up the challenge.
Is there any? Yeah, Mark.
Yeah, I have some follow-on comments to that, Alicia. Excellent comments. The one that I want to pick up on, I think it really goes to creating, I guess, a connection with all the dispersed groups that are tackling this. The two that you mentioned, Holger, are geothermal and nuclear. And one of the things that I've realized through Mission Innovation and through the Innovation Challenge 6, developing a platform that serves all the needs across a diverse set of materials has allowed us to connect geothermal and say that we did it through heating and cooling. We're looking at thermal energy storage materials, because again, we go back to materials for their technical challenges. And so we connected strongly with them. We presented to the IEA nuclear group in Paris during one of their meetings to talk about how we could support materials development in the nuclear. And so when we realized what we wanted to do in Mission Innovation and Innovation Challenge 6 originally, it was to create a platform that spans the diverse needs of the community. And that doesn't mean we do everything. We pick or we prioritize, we pick the ones that are low-hanging fruit. Alicia mentioned low-hanging fruit earlier. And so that platform, that broad platform, generic platform that could apply to many different problems, and then we select them, we down select, allows us to really make an impact on clean energy. And so I wanted to stress the fact that there are ways of connecting these diverse groups that have challenges that are working, geothermal and nuclear and organic solar cells and everything else, through a common platform like the maps. And so that's one way. And then all of the other stuff we've talked about in this workshop bring together absolute important facets along that value chain. So maybe that's the last thought that I can come up with.
Okay, thank you. We have 1 minute left. Francesco, do you want to have the final comment?
As a final comment, I think that from the policy point of view, what is really relevant is to make, I think, a strategy behind the money you are giving. I think that, I don't know if it will work. We are an experiment as program managers. In the next days, that means 3 months, it will be employed 6 more. We have been copied by AMPEA approach, and we have been pasted in a different way, because you can copy, but you have to not to do Control-C, Command-V, but you have to change because the ecosystem is different. So we are brand new. We try to connect many of the people that are here, Mark and Olga. We already interviewed them just to open our knowledge and their knowledge. The same I will try not to stress, but I will call Alicia. And I feel that the policy has to evolve. You cannot put in place a European Innovation Council without considering mistakes. But just to conclude, doing a citation, when they ask me what is the peculiarity of deep tech, I like to say that we have to use this clear definition that is the DBTL approach, that is design, build, test, and learn. The last L, in my opinion, it's the most important. That means we have to learn from our mistakes. EIC will try to do a double funding that is a top-down and a bottom-up. Top-down means that we take the responsibility as program managers to identify topics, obviously speaking with everybody, but we take the responsibility. And to conclude, I feel that if there is a top management inside the policymakers that has got the knowledge, or that has got the team that might have the knowledge, that's a good way also to give the very famous ambidexterial look. That means if the companies must have the short view, the policy might also have the long term. It's not so common in Europe, but I hope we will be able to do.
Okay, thank you. I think Sako has a question now. Sako, please.
Yes, thank you. Yeah, my question was a little too long to type. So thank you very much for this very interesting discussions. I fully see the importance and the urgency of instilling such mindset of entrepreneurship through a targeted, focused programs for especially targeted more toward young researchers, of course. But the current structure, the research structure that I am aware of in Europe, especially in France, is quite vertical and rigid. And I work with many among my peers who do not consider entrepreneurship to be part of their job description. And they are even against it as if it would defy their religion. Whereas those are the ones who hold the key, or they have the stronger position in the different institutions. We working in energy materials probably can get out of it faster because we have this pressing need of energy transition and clean climate goals 2030, which is basically a month from now. But how can we, maybe it's a question to Francesco, what can Europe do to break down this rigidity of the cultural mindset in Europe, how the scientists should do scientists, sitting at the top of the knowledge pyramid and handing down the knowledge and making money and creating business is for the lower or the different class of people. Is there any initiative within Europe really to overhaul this, or do we have to wait for our generation to die out?
I don't think that you have to die out. Science will always be science. And I feel that to make, I feel that this word has been created by US guys from MIT. They call them entrepreneurial scientists, Sacco. And to be an entrepreneurial scientist, I feel that you are never too old, but you have to love the money. I will always remember one fact, Sacco, that I was in a big meeting. I'm speaking about my country, Italy. And there were really hundreds of people, and we organized this meeting where there were scientists saying good things. And at a certain point, the scientist said, yeah, because, okay, yeah, we need the money, but we need the science to be done. And it was a meeting on making money out of science. The speaker after, it is a friend of mine, and he's a VC founder. And he jumped on the chair, and when he had to talk, and he said, hey guys, I am the bad guy. I am the guy that has got the money. That horrible thing. It's horrible money, but without money, you cannot do science. And so I feel that if the motivation of the person is to make science, it's wonderful. He has to do the scientist. If he has got a little flame to love the money, he should look at this. I don't want to make it easy. I feel that, okay, the goal of innovation has to be the improving the quality of life. Okay, that's good. But somehow, in my opinion, the knowledge and the appreciation of how to make the money is something that you can learn, but if you do not have and you do not learn, it's better if you keep on doing the scientists, because there is always room for scientists, in my humble opinion. And to answer you, it exists something, European Commission? Yes, there are many programs on training. Also now on the other laptop, we are doing this boot camp Pathfinder. I feel that you join one of these, Sacco. And yeah, but they are not enough in the end. It has to be, in my opinion, something that I want to be philosophical. It has to come from the people to say, okay, now I don't do anymore the scientist, I do the entrepreneurial scientist.
So I need to jump in there, although there's pieces that I definitely agree with you. And you know, the MIT ecosystem is one that I've both studied in and have studied. I posted a paper that there's a free copy of there from the NIH about an entrepreneurial scientist, Bob Langer, chemical engineer, most cited chemical engineer in history. You know, had 30 spinouts out of his lab at the time that I studied his lab. You know, out of 393 issued patents. Incredible publication record, star scientist in every sense, not in love with the money, in love with impact. You see all the people that you know, have responded to the pandemic, and you see all of the science-based ventures which were critical to partner with the pharmaceutical companies. Excellent analogy to the situation we face here. And all of those spinouts in every of the ambitious vaccines, it came from a research lab. It came from a spinout who may have been out for less than 10 years. Moderna never had a product out before, also partially out of the Langer lab and partially out of the Rossi lab. Here in Vancouver, out of UBC, Peter Cullis and the many pieces of spinoff that came to be Acuitas, including failed companies, has the lipid nanoparticle that's used by both the Pfizer vaccine and also arguably the Moderna vaccine. There's a lawsuit there between former collaborators. And then you look at, you know, in every case there, those scientists that were driving those vaccine development long before it was fashionable, when they were thought to be crazy, they were not doing it for the money. They were doing it to make impact. So absolutely, some scientists love the money. There is another path for scientists who probably not going to be the CEO. In fact, I don't think they should be, but they're going to be either on the board, the scientific advisor, a co-founder scientist. They may become the CSO. But for example, Bob Langer says he spends 6 hours a week on his companies, and he has, you know, now 30 and counting of what he's co-founded. So I would say two things. One, that scientists are motivated often in this in the more than 150 science-based spin-offs that I've studied. They're often motivated by providing jobs for their grad students, and they're motivated by creating impact from their science. And so that's a whole other path. And the second thing I would say is you can change culture. It's a hard process, and it has to start at the top. But a way that I found in the 7 years since we started the Invention to Innovation program in my university, because we started as a 4-credit program, and we had to take it through Senate, and we had to, convince the PIs to let go of their grad students and postdocs 1 night a week to come down to our campus, and we've multiple campus institution. In doing so, we actually started to convert the PIs. So those grad students would go back to their labs, and they would tell the lab the things that they've learned about the strategy that could help the lab's commercialization strategy. And so we have several Canada Research Chairs who actually enroll in the 4-credit course. This year we have 3, 3 professors, one of whom in this year's cohort is a Canada Research Chair. But they're coming in because their grad students told them that there was things they could learn. And they don't have to take the training themselves, but if you get the right people in the lab that are learning things that are useful to the lab, that are going to help secure translational research grants, that are going to help create strategic alliance partners, I think the culture will change.
Okay, thank you, Alice. I think, Lorenzo, we should go to the next point on the agenda.
No, definitely, yes, because now we are 25.
Thank you to all of you, first of all.
But I think it was a very interesting discussion, so I thought it was really a pity to stop it just because of 10 minutes. So
I will be quite short here now with the conclusions, because I think that was one of the objectives to have this panel session, to some kind of conclusions. I would just be short here. First of all, I think it's clear here from this workshop that material is key to many things. Combat climate change, clearly it was mentioned 80%, but many other factors also. Also the problem that now it takes 20 years to develop, and that needs to be reduced. It was 20 to 2 said, now that's not possible, but maybe 20 to 5. And so we have to realize the specifics, that it's not like developing the apps. Now, what are the keys to do these things? There is one which is very clear here, is that you need some interdisciplinarity. You need different people. You need a scientist, this thinking out of the box. And but something I had one of the questions for when I was thinking about the panel here was this: is this cross-cutting? Are we the same, sharing the issues? And for me, the conclusion is yes. So we can have this common platforms. We are sharing many of the issues in the material science. I think nuclear people and windmills or PVs or whatever, there's a lot to work together, actually, in the scientist part. It's also being stressed here many times that it's very important to link up with the customer early on, and also have the feedback from the customer in the process, and not overdo the science. So you don't need to be perfect. Involve the customers in the process. And then, of course, now if we're going to bring this 20 to 2, there are also the new tools that we need for that. And a lot of this is, of course, related to digitalization. It was mentioned here. So we need to accelerate the process, 20 to 5, and clearly digitalization has a key part there: artificial intelligence, machine learning, digital twins, big data, that's part of it. But we also need to develop, a lot of the time is also testing. So we need to accelerate the testing itself, new ways of doing it. For instance, testing micro instead of macro, etc. That is more difficult, I think. Also, the simulations is also one part of reducing this development time. Some of the testing can be replaced or at least complemented more by modeling. I think that is. Then there was also something discussed here about regulation. We expected actually regulation to be identified as a major bottleneck, but it was not. But in certain sectors, like nuclear in particular, it is to qualify materials and so on. And then it was here a bit mentioned about politics. Politics can help. Politics can also do the opposite. And personally, one reflection about hydrogen was mentioned. Now we hear, I've been now quite some years in the JRC, 20 years. I remember, like, so things go in waves. 15 years ago, everyone talked about hydrogen, at least in the JRC. Then, like 10 years ago, it was almost dead. No one talked about hydrogen, and now it's on top of the agenda again. So I think we need to have the broad picture and not always follow the trends. And that is something I think when media or politics and sometimes drive things too much, sometimes it can be that things are more or less trendy. And with this, I would, and into just final comments here, I think this has been a very successful workshop. I think we have seen both a number of presentations giving, let's say, the broader picture. And we also had a number of very interesting presentations giving the examples of starting from the research, going in different ways. We are at the tier level 5, 6, or in some cases we are really at the industrial production. So I'm very happy that this this workshop has worked out so well. And now I think Sacco will give some final slides also about information of the next workshop. So I give the word to you.
Okay, great. Thank you, Kelly. So, and thank you very much, Kelly, for being the organizing chair of the second workshop. We have changed the format. Previously was just a half day, and you have winged it, this 2 half days with participants all the way from Vancouver with 9 hours of time difference. And thank you, Alicia, for waking up so early. And also Mark, I believe you're joining from more or less on the East Coast, but nevertheless, I know the time difference is not that easy to handle when you're not a morning person. So today was the second, yesterday and today we had the second of the webinar of the workshop series of EERA's Energy Materials for Innovation Initiative. So let me say that, as I have said, this workshop is consisting of 6 different webinar series. First one took place 3 months ago in July on materials discovery and development. And now we have done the from lab to engineering, manufacturing. The next one will be given in the beginning of December, approaches for the implementation of digital twins. So now we are moving up from discovery to manufacturing, and now we're tackling the device themselves using the digital twin methodology. The organized committee chair would be Rafael Mayo Garcia. And in 2022, we have 3 more, the dates to be determined. First one on materials under harsh conditions. Then the sustainability in materials, very much of an important issue if you want to bring materials into the market for the long-term use. Then the catalysis in cross-cutting applications. And the final conference we hope to hold in person in Brussels, which will be a more of a strategic conference, inviting policymakers and not only scientists, summing up the takeaways of all these 6 workshop series. And we hope to produce a white paper on energy materials and bring it to the forefront of the energy research in European research landscape. So just a little bit more, few more words, because Rafael is not here with us today. So it will be me, the organization committee chair, Rafael from CMAT. He is now with his organization committee members from DTU, FCJ, IZFP, Fraunhofer, University of Lorraine, and VTT. They are composing all the invited speakers and the formats. So please be aware that we have this going on and come back and check with us from time to time. So these are the to be finalized topics. There are several of them. And of course, there will be many more depending on the suggestions from the workshop organizing committee. So here are some useful links and information if you want to keep informed on the development and the progress of our workshop series. There is a one-stop link on the EERA's website, EERA-set.eu. And if you go to the events section, you will find all the information on the EERA initiated events, not just our workshop series, but many others. And please follow also the EERA's LinkedIn page, where they will be announcing each time there is something new going on in EERA and in the related organizations such as IEA. And we also have a Twitter account of EERA, the same message. You can get some information. So if you have a Twitter account, don't forget to follow us so you can get the latest information from EERA, including our workshop series. So the presentation today is recorded, as you know. EERA will be editing some, and they will put it on the YouTube channel of EERA. So the recording from the first workshop is already available, which was on the materials discovery and development. So the link will be sent automatically to all the registered participants of today. So you will be receiving when the video is ready in your mailbox. If not, please come back and check on the EERA's YouTube page, or to send myself or Kelly an email, and we'll let you know where the video recording formatting is. So that's it from the EERA workshop series organization side, unless Lorenzo or Monica has something to add. So I'd like to thank everybody, all the speakers, for your great and very thoughtful presentations, and also the debate, the panel session discussions, as well as the participants who have actively asked questions and those who remained silent but listened to us all the way till the end. So thank you for your attention, and I hope to find you all back in December at our third workshop series.